Okay, I'm beginning to record.
Okay, start.
Okay, so welcome to the first session of Tuesday of the second day of the conference. This session is on signatures encryption and algebraic construction. And the first talk of the session is simple and efficient lattice CCA secure KEM and a standard model by Xavier Boyan, Malika Isaba Kene, and Kinyu Lee. And Kinyu Lee, I assume, will be giving the talk. Thank you. We don't hear you. You're muted, and we don't see your slides.
Okay. Good. So thank you. You can hear me now, right?
Yes, but we don't see the slides.
Yeah. So I need to share the screen, right?
Yes.
Let me see where. Where is it? Sorry.
On the bottom, share screen button.
Sure. Yeah, here. How does that look like?
Yeah, we see the entire screen. Yeah.
Yeah. Yeah. Okay.
Okay, you have about 10 minutes, including questions.
Okay. Okay. Thank you. So hello everyone. My name is Qinyi Li. I'm from Griffith University, Australia. So I'm here to present our paper, a simple and efficient CCA secure lattice KEM in the standard model. This is joint work with Xavier and Malika. So our contribution is a simple construction of adaptively chosen ciphertext secure key encapsulation mechanism from lattices, and is secure under LWE problem in the standard model. And our construction doesn't use any generic transformations, no one-time signatures or message authentication code. And our construction is efficient as the best low lattice non-adaptive the chosen ciphertext secure public key encryption proposed by Michangio and Peikert in 2012. So first of all, our construction is based on the Michangio and Peikert CCA1 public key encryption. So here the capital letters are matrices and lowercase letters are vectors. So the public key consists of 3 matrices in that scheme. So A, A1, and G. And the private key is the is the low matrix R. So yeah, so to encrypt, the idea is that you have a tag and construct a LWE type of ciphertext, and to decrypt, we can use the Michangio-Peikert gadget trapdoor to recover the LWE secret or noise. Yeah, so it is not CCA2 secure or not adaptively chosen ciphertext secure. It's because the ciphertext is essentially malleable. So if you look at ciphertext, the attacker can try to modify the ciphertext and send the modified challenge ciphertext to the decryption oracle, and the security proof has to stop. So there are essentially, in general, there are 2 ways to do this. First of all, the attacker can do some re-randomization, changing the secret of the LWE sample, or the attacker can add some noise to, because LWE noise, if you add a little bit on top of that already small noise, you still get small noise, so the ciphertext is still valid. So in our construction, essentially we add one extra matrix U. So essentially what we do is that we do essentially a similar thing, but we compute this tag by the hash of part of the ciphertext and the U times E1, which is the cis hash of the noise E1. So essentially by doing this, we end up with roughly with exactly the same ciphertext size. But the idea here is that because we compute this tag so this tag comes from the hash of the ciphertext and the sys hash of the noise. Then if you want to change any part of ciphertext, you have to change the tag. So the simulator in the security proof can answer the decryption query. So that is the idea. And to show that the system is secure, we need to take care of this U times E1 because T comes from U times E1 as well. So T might leak some information about the LWE noise, but we sort of apply some tricks to let the proof go through. So that's my talk. Thank you. Thank you. Yeah.
Thank you. Let's see if people have questions. So the way that we the attendees cannot speak to maintain sanity in the conference.
Okay.
But there is a Q&A and a chat, but so far there are no questions.
Sure.
The panelists can speak, and I invite panelists to also speak.
Okay.
So I don't work in this area, and the presentation was short enough to like, okay, that for me.
Yeah,
that's how it works. Okay. No, of course,
yeah,
of course.
It's very technical. Sorry. So this, yeah, sorry. Yeah.
No, I mean that's how it's supposed to be. It's just a couple of minutes, and
sure. Yeah. So hopefully, if you guys have questions, go to the YouTube videos uploaded by the conference and send email to me. I'm happy to answer that. Yeah, thank you.
Okay, so what we're also gonna do, so can you, if you want to stay until the end of the session, if people come up with more questions in the end, we can have I'm gonna ask questions to all the speakers of the session.
Sure,
okay?
sure. I'm trying. Thank you.
Okay.
Yeah.
Okay. All right. Let's move on to the next paper.
Okay,
The next.
Stop sharing.
Yeah. Stop sharing. Thank you. The next paper of the session is double authentication preventing signatures in the standard model by Dario Catalano, Georg Fußbauer, and Azam Soleimanian. And Azam, I think, is giving a talk. Hello, yeah. Azam.
Hello. Let me start sharing. Just a moment. Hello, everybody. I'm Azam, and this is a short presentation of our work, double authentication preventing signatures in the standard model, which is a joint work with Dario and Georg. In this presentation, I'm using DAPS as the abbreviation for double authentication preventing signature. And what is DAPS? It's a kind of signature scheme where message has two parts, address and payload. And the signer is considered to behave maliciously if he or she tries to sign two messages of the same address, but two different payloads, which in this case, we penalize signer how it would be possible for others to extract information about the signing key. So you can say that syntactically it's similar to digital signature as you see, but it also has this extra algorithm, which is extractor and can extract the signing key from malicious messages. And in the sense of application, it can be used, for example, in cryptocurrency when a malicious sender tries to sign the same coin for two different receivers, which is called, this is called double spending, which should be avoided. It's very dangerous. For the contribution, what we have done, we have designed a kind of a general DAPS construction, which can support exponentially large address space. It is also secure in an untrusted setup where the signer can choose its own key. And it's based on a standard assumption like CDH, discrete log, and there is no random oracle. And note that most of the previous works are mainly in the random oracle model, but this our work is in a standard model. Before going to construction, we are using two main building blocks: vector commitment, which is a commitment scheme that you commit to a vector instead of a single value. And later you can open it to a specific position. And the nice point is that the opening does not depend to the length of the vector. And the other primitive is double Camelon hash, which is a collision resistant hash with two trapdoors. So basically it is hard to find collision unless you have one of the trapdoors. Now let's go to the construction. Our construction is a flat tree based construction. Verification key is fixed as the value of the root, and by the address part you find the position of a leaf, and you go through this path, you assign some values to this path to the root, and your signature would be simply the concatenation these values. But what are these values? This is like a Merkle tree when for each node you commit to the children of the node by a hash function, collision resistant hash function. But here we are instead using vector commitment, which can do the same task in a more efficient way. And we also are using double Camelon hash to connect your current path to an existing path when you arrive to a node that you already have visited. So you kind of find a collision and you just connect these two paths together. It was the big picture of our construction. And for the instantiation of building blocks vector commitment, we are using the scheme of Catalano-Fiore, which is based on CDH assumption, but it is only secure in trusted setup where the key has to be generated honestly. And for double Camelon hash, we present our own instantiation, which is based on discrete logarithm assumption, and it is secure also in untrusted setup. So one of the building block is secure in untrusted setup, while the other one is not. How we can have DAPS in untrusted setup? Well, we simply replace vector commitment with a usual collision resistant hash function with the cost of a longest signature. So here, a natural question, open question is that, can we have vector commitment scheme which is secure in untrusted setup? And that's it from me. Thanks for listening.
Thank you, Azam. People have questions? Let's give a few seconds, a minute. So while people are thinking, I was wondering, so the application to the cryptocurrencies, is that like really generic of the signature? I guess what you would be doing is, because existing cryptocurrencies, of course, deal with this kind of stuff, right? With the issue of signing to different people. So that wouldn't help much to existing one, but I guess it gives an opportunity to design a cheaper cryptocurrency if you base on signatures like yours.
It depends which system you're using. For example, in blockchain, it's all in Bitcoin, sorry, it's already secure against double spending.
Yes.
So it depends in which system you're gonna use it. But still, for Bitcoin, it has a kind of possibility also, because in Bitcoin, you don't need this kind of signature because everything is validated by others. But
Yes.
to validate and be sure of that double spending is not happen, you need to wait for 6 blocks, and each block takes like 10 minutes. So you have to wait 1 hour So
Yes.
it's not proper for some service that you want to receive the answer immediately. Or for example, if you are the person who are receiving the second payment, you would not be happy because you don't receive anything. So still you can use this signature even for this kind of structure, I think. Because
Okay, I'm trying to think.
so then you don't need to wait.
Well, so I don't know if you really don't need to wait, but maybe you can wait a little shorter, because there could be different problems that will arise if you don't wait for 6 blocks, right? I mean, the problem, yes, if you don't wait for 6 blocks, what happens is that your history can be erased, or whatever, not necessarily 6, but some number of blocks, right? Somebody can construct a longer chain, and whatever you've deposited on the chain, whatever signatures, whatever transactions you've put, they can be eliminated. But if your secret key is extracted, I guess there is a sufficient disincentive for you to do that. But on the other hand, if your secret key, like in a blockchain, if your secret key only manages that wallet, and that wallet doesn't have, it's not your permanent wallet that with a lot of money, if it's just like in a Bitcoin.
You use signature actually for another deposit, not probably for your wallet, for another deposit, and you define some sessions, and you would say that for this session, if double spending has not happened, you can retrieve your money from the deposit. So you need to
right. So you would be
time
some
for sessions and these things, yeah.
Okay. Yeah. Okay. So there's a comment on chat from Pino. He wanted to ask if this is related to Sigma protocol. If you have the same first message but 2 different challenges, then it's possible to extract the witness.
Exactly. As you see, this is a similar concept, because you have the similar concept also in Sigma protocol, that if you have the same things, then something would be extracted. Actually, there are some DAPS signature from Sigma protocols, but there you need, because Sigma, in this kind of protocol, you need interactions. So you use a kind of fiat Shamir transformation to have it in a non-interactive way. But here we are not using any random oracle assumption, and this was the point of the paper.
Okay, Pino is happy with the answer. He thanks you. Okay, I see that Helger is here, so Helger can take over the session. Helger, is that right? If not, I'm going to continue. Okay, well, I don't hear yet from Helger, so I'm going to continue with the session. The next paper of the session is efficient signatures on randomizable ciphertext by Balthasar Bauer and Georg Fuchsbauer. And who's giving the talk? Balthasar, I think, is giving the talk. Go ahead, unmute, turn on video, turn on your slides.
Yes, I am giving the talk.
Okay, go ahead.
So, do you hear me well?
Yes, we hear you. We see you. We see your slides. Go ahead.
Okay. Okay. So hello everybody. I am Balthasar Bauer, and I'm happy to present you efficient signatures on randomizable ciphertext, a joint work with Georg Fuchsbauer. To introduce our paper, I would like to present you a primitive called delegatable anonymous credentials. In this primitive, there is one authority which can give some credential to one user of the system, and then from this credential, the user can give a credential of second order to another user of the system. And the main security property of these schemes authorize the users to prove the validity of their credential without revealing their identity. And to build such primitive, many works are using equivalence class signatures. This primitive is very analog to standard signatures, except that in this context, the messages are vectors of group elements. And when someone signs a message, it does not sign only one message, but a whole class, the class of this message. What do I mean when I say that? I mean that if someone has a signature, a valid signature for one message, M, he can, from this message and without knowing the signing key, create a valid signature for a message RM with R arbitrary non-zero scalar. And to understand well why this primitive is useful to build a delegable anonymous credential, I can show you a toy example. It's not a real scheme, but just an example to understand the idea. If the identity of the user is the vectors of group elements, then the authority can sign it. And now if the user wants to show the validity of his credential anonymously, he can randomize his identity and adapt the signature of the authority. And because he has randomized his identity by multiplying by a scalar, his identity is not known by the viewers. But there is one issue in this construction, is if someone has built the vector's identity, then he can recognize it even it has been randomized. And to fix this, we decide to use a more complex primitive. It's very analogous to equivalence class signatures, but in this this more complex primitive, the messages are now ciphertext and not plain text. And now when we say that two elements are in the same equivalence class, it means that they contain the same plain text. So of course, this primitive is more complex because we have to add encryption functionalities, because now there is ciphertext. And for another reason, it's also because now equivalence class depends of encryption key. And for this reason, we have to use new definitions. So we have built such scheme, and it verifies all the correctness and security properties we want. And in particular, in particular, we have proven that our scheme verifies the new enforceability properties defined in the generic group model. So we could be very happy because our scheme is secure, correct, and also efficient in the sense that the signatures are very small. But unfortunately, our verification keys are too big to use it to use our scheme in delegatable anonymous credentials context. But as a good news, it seems useful for other primitives such as evoting. I would like to thank you for your attention, and I wish you a good day. Hello?
Thank you, Balthazar. Let's see. So Helga is going to take over this session sometime soon. Let's see if, yeah, go ahead, Helga.
Yeah, I can take, yes. Sorry for being late. The virtual conference thing really doesn't work for me, especially because we also have home office right now. So thank you very much, Vlad, that you took care of the first talks. I have to say that I currently don't have any questions myself because I just arrived at the beginning of this talk. So I would just, anybody else who has a question or two to Balthazar? Anybody? Hello? Okay, I guess.
So maybe I missed it.
Vlad.
Yeah, maybe I missed it, but I was curious. What are applications of these randomized signatures? Randomizable ciphertext signatures on randomizable ciphertext. How is it?
So no, I'm not an expert in e-voting, but I've just spoken with people. We are building primitives in e-voting, and they told me that it could be useful in their primitive, but unfortunately, I could not say any more about this specific application.
How, for example, how it would be used in e-voting, right? What's the feature that is very important?
A good thing is, for example, when you randomize the ciphertext, it's the fact that, for example, you could have, for example, the receipt-free property easily, because
is there unlinkability, some kind of unlinkability?
Sorry?
Some kind of unlinkability?
Yeah, exactly. I don't know how to say, but the fact that yeah, you can randomize the ciphertext and the signature at the same time is a good thing in a e-voting context, because and of course with a valid signature.
Okay, thank you.
So I think in my like from my point of view, I can imagine that randomized signatures are very useful even in the case of a usual mixnet, where you get in ciphertext and then you re-randomize them and output them in a different order, and then maybe you can somehow simplify the shuffle argument by using the fact that everything is signed. So I imagine that they are useful there, but it's a good question. I've actually never checked it. So at least I can see some applications. So any more questions? So if not, then let's thank the speaker. And the next talk maybe can start. The next talk is fast threshold easy DSA with honest majority by Ivan, Thomas, Jesper, Jakob, and Michael. So Balthazar, you have to stop sharing your slides.
Yeah, I think Balthazar, I think on the top maybe there is an unshare button. Let me see if I can kick him out. I mean, not kick him out, but unshare him. I don't see. Oh, there we go.
I did it.
Okay, thank you.
Okay, thank you. So I understand Thomas is going to present it.
Yeah.
Please.
So I'm trying to share my screen. Okay. So do you see the screen?
Yes.
Yes.
Okay. Good. Okay. Yeah. So yeah, I'm going to present this fast threshold ECDSA with honest majority. And first, just a brief recap of ECDSA and threshold ECDSA. So in this setting, we have a number of servers, and we have a private key X, which is secret shared among the servers. Everyone has a public key here. And then to sign a message M, we have to compute some values here. We have to pick a nonce. It's a random value, and it has to be kept secret. But we have to open this value here. And also to compute the signature, we have to compute this expression. And the hard part with the threshold ECDSA is that we have to compute multiplications of secret values. This is the private key, the private signing key, and this is the nonce inverted. So it's hard because there has to be some MPC multiplication going on here. So if we look at previous work, it's obvious that this can be done by like general MPC from the 80s. Also in 96, Gennaro and others, they came up with a solution for honest majority based on error correcting codes. And then in 2001, there was a two-party solution. And from 2016 and onwards, there's been kind of an explosion of threshold ECDSA solutions. And it's obviously it's because of the application in cryptocurrencies. There's been a lot of recent interest. So all of the results here, they're for the dishonest setting, and they rely on like heavy stuff like OT extension and homomorphic encryption, even though the most recent results are quite efficient. So the question that we ask is whether the case of honest majority is completely settled with this result from 96. And the answer is, of course, no, because we have some improvements. So before I just briefly explain our solution, I just want to point out some properties of threshold ECDSA that has gained recent interest, because when we try to use threshold ECDSA in the real world, it turns out that there are some nice things that we want. One of them is this online-offline thing. It turns out that in ECDSA, a lot of the work can be pushed to the offline phase, so we can generate so-called pre-signatures. And then when we do that, only very little work has to be done online, and that's very practical. And if we take this to the extreme, we can even sometimes gain what we call non-interactive online signing. So this is where we do some work in the offline phase, and then in the online phase, the servers that has to produce the signature, they don't even need to talk to each other. And this is very useful for in the cryptocurrency community. People like to hold their secret stuff in a cold store, disconnected from the network. So this is very nice to have. Also, there's been recent interest in signing with a large number of parties. And again, this comes from applications in the cryptocurrency community. In fact, there's been some a fancy cross cryptocurrency solution that needs this signing with a lot of parties. And this means that properties such as identifiable abort and guaranteed output delivery suddenly becomes quite important, because if you want to sign with like 200 out of 500 parties, you really need to be able to continue even if there's a few malicious parties. So in our case, we had some business requirements. There was a customer who wanted to do 3PC, like a threshold ECDSA with 3 parties. There was a high focus on high performance, and we had to do a good proof of security. On the other hand, it was okay that it was honest majority with the board. So we looked at this result from 96, but it turns out the thresholds there are not really good for 3 parties. In fact, there has to be at least 5 parties just to run the protocol. There's also in the paper, they sketch a solution for that works if the number of parties is at least 3t plus 1, T is the security threshold. But still, this doesn't work for 3 parties. There is kind of an implicit solution for 3 parties with a board in that paper, but it turns out that it still requires a lot of heavy computation. In fact, we have to do 35 long curve exponentiations for 1 signature. So we came up with a new, we had a trick that lets us kind of verify the correctness of one of those multiplications of secret values that we have to do. It reveals one of the factors in the exponent, but that's okay because we have to do that in ECDSA anyway. And the result is a solution that works for 2t plus 1, which means that it works for 3 parties in particular. And it's more simple and it's more efficient. So we actually came up with 2 versions. The first one is very fast. We avoid any use of Peterson commitments. When running with 3 parties, I mean 3 servers for doing the signature, we only require 5 long exponentiations, which is like something around 14% of the previous result of Gennaro. And then we have a full UC proof, in fact, with perfect security. We also came up with a kind of an extension. So here we accept to do a little more work in the pre-processing phase. And what we gain is guaranteed output delivery in the online phase. And also the online phase is non-interactive. So finally, I just want to mention that we are not the only one thinking about these issues. In fact, there's been several results on ePrint and otherwhere recently that takes like recent results. In these cases, it's for dishonest majority and then adds those new properties of identifiable abroad and non-interactive online. There's also been some cool results showing that doing ECDSA using general NPC is actually not as inefficient as people believed just a few years ago. So that completes my talk. Thank you.
Thank you, Thomas. I have like 2 questions myself. So the first one is that I understand your motivation very well. Like ECDSA is a standardized signature scheme, so it's very important to have a threshold version of it. What I don't understand is what is the relation to cryptocurrencies. So maybe you can, first of all, explain what exactly is signed in a threshold manner. And the second question is that why do you need ECDSA there? Because I think one of the nice things about cryptocurrencies is that it has given birth to a lot of new cryptos. So for example, this so-called snark-friendly hash functions, for example. So how does your solution compare to threshold version of some other signature schemes?
Yeah, okay, thank you. So the first question, why we need threshold signatures in cryptocurrency. It turns out that most cryptocurrencies, they're based on a blockchain, which is essentially just a big public database with the consensus. And the currency works by, like, you have some coins, and then when you want to transfer the coins to another person, you basically just sign a statement saying, I transfer some money to another guy. So you need to sign something in order to make a transaction. So that's where the signature comes in. Mm-hmm. So it's like most cryptocurrencies they have those two layers. The low layer is the blockchain, and then on top of that you have signatures. You have a long chain of signatures saying, okay, my money, now I want to transfer like 1 Bitcoin to another person, and then I sign this statement. So only I can transfer my money because I know my private key for signing. And the other...
threshold?
Sorry?
Why do you need threshold there?
So basically, you don't need that, but it just has turned out that especially there are some cryptocurrency exchanges where a lot of transactions go on. And it's very sensitive because if you break into this exchange, and it's very easy to steal the signing keys. So there's been a long chain of attacks where a lot of cryptocurrencies has leaked because the private keys were simply stolen from a single computer. So the reason why threshold signatures has become popular is because we want to add a layer of security by taking the private key that actually more or less corresponds to your bitcoins or your cryptocurrency money, and then split the key in pieces and put those keys different places, because then the hacker has to break into several computers in order to steal the key.
Mm-hmm.
So it's a way to add security.
Also, just one comment, maybe you can stop sharing your screen. I'm looking at very strange version of myself. Okay. Then the second question?
Yeah, the reason for ECDSA is basically that the most popular blockchain cryptocurrencies like Bitcoin and Ethereum, they are based on ECDSA.
Mm-hmm.
So in order to provide threshold solutions for those, it has to be ECDSA. And you're right that the most recent, most modern blockchains, they start to use other signatures that are more well suited for doing threshold. We still have to, I mean, most cryptocurrency transactions still happen on for instance, the good old Bitcoin.
Mm-hmm.
But I guess in the future, we'll see more signature schemes implemented in blockchain, in cryptocurrencies that are more threshold friendly, so to say.
Do you have a comparison between your scheme and some other threshold signatures of like not the ECDSA, but something else?
Yeah, not really.
Okay.
It would be, I mean, there are, for instance, there's also the DSA signature scheme, which is being used in, for instance, part of Ethereum. But this DSA is much more efficient. So, I mean, the comparison is, in a sense, it's quite easy because, for instance, the DSA signature is just much more efficient. You don't need any communication between the servers in order to produce the signature. So it makes most sense to compare against other ECDSA solutions.
Okay. So yeah, like I said in the beginning, I well understand the motivation because ECDSA is the standard signature scheme, but it seems that your work is heavily motivated by cryptocurrencies. So that's why I asked. Does anybody else have a question? I'm new to session sharing, so I guess you have to raise your hand or post on chat.
So just a really quick question. At the high level, how does your scheme compare to several other threshold ECDSA schemes? Like, what's the main advantage? I guess you have honest majority and you're faster. That's what you're saying, right?
Yeah, basically we're, I mean, the only scheme that really makes sense to compare against ours is the one by Gennaro from 1996, because it's in the same model, right? And if we do that comparison, it turns out that we are, like, regarding local computation, we're like 7 times faster for 3 parties, and that means that we can gain a signature throughput that is 7 times faster.
And in terms of like simplicity and the ease of implementation and so on, is that a concern? I mean, it should be concern in practice, but how does your paper compare to Gennaro at all?
So in terms of simplicity,
I
would say that ours is certainly more simple, but we also, like, it's 2 different models. They cast their scheme in the full security model with like guaranteed output delivery. So it also means they have to do stuff in order to fix things if someone doesn't do as intended. In our case, we can just abort.
But you mentioned that we need to deal with aborts, right? If you have, so this is your second, I guess your second version.
Yeah, it's the second variant.
Okay.
Yeah, it gets, then we take one step towards something that's a bit more complicated.
Okay, thank you. Sorry,
Okay.
I think we need to move on because we're going to
Yeah.
run out of time otherwise.
Thank you.
Thanks, Thomas. Thanks.
Yes, thanks a lot. And the last talk of this session is short threshold dynamic group signatures by Jan, Manu, Anya, Gregory, and Patrick.
Yes, I'm Patrick, and I'm presenting the talk.
Yeah, please.
Yeah, hold on. I'm just trying to share my screen. So I assume you can see it now.
Yes.
You still see it? Okay.
It's gray.
Ah, it's gray. Okay. I think it's because of skim. Let me try with PowerPoint. I will stop the share and try with PowerPoint instead. Okay, so now you should be able to see. Now it should be working.
Yeah, now it works. Yes, thanks. Please go on.
Okay, so this presentation is on short threshold dynamic group signatures. It's based on joint work with Jan Kamenisch, Manu Drivers, Anja Lehmann, and Gregory Nevin. So just a small reminder, dynamic group signatures are really fundamental in cryptography, as it's a primitive which allows users of members of a user group to anonymously sign on behalf of the group after being added by an issuer. And this means that anybody can verify that a signature was computed by a group member, but only a dedicated authority called opener can infer any information about a signer. And the anonymity requirement of such a scheme is that as long as the opener is honest, and even if the issuer is corrupt, no party can infer any information about a signer. And no computationally bounded adversary, more precisely. And the traceability requirement states that no computationally bounded adversary should be able to compute a signature, should be able to forge a signature. That means that to compute a valid signature, an adversary must have corrupt group member, that the user that has already joined the group. And meaning that normally an adversary should not be able to forge a signature, and that the opener should always be able to recover, and that the signature should always open to a valid group member. And in certain definitions and schemes, the roles of issuer and opener are actually combined. This is, for instance, the case for the most efficient schemes, as I will mention them later. And in this case, then the single authority is referred to as group manager. And group signatures have very large scope of applications. So for instance, vehicular communication networks, in which vehicles must be able to anonymously authenticate the messages they exchange, but without being traceable by eavesdroppers. And for instance, the trusted party modules, which must be able to certify that certain messages were computed by accredited devices, but without revealing any information beyond that. So given these requirements, one can see how the anonymity requirements of group signatures really fit the bill in this case. But the odd thing about the definitions of group signatures so far is that even though privacy is really the main concern of group signatures, the authority is a single point of failures. And in general, in cryptography, like we saw in the previous talk, like whenever privacy or even just security is at stake, usually what people try to do is to distribute the powers of the parties and not really rely on a single one. So to minimize as much as possible the trust assumptions. And this is basically the goal of the paper. But not only, the goal is also, is to distribute the roles of issuer and opener, keep them separate and not joined as I mentioned before with single group managers. So to reduce even further the trust assumptions, and have both issuance and opening, having both of them being threshold. And so that the scheme remains secure as long as a certain amount of issue or of authorities are corrupt, but not all. But it's not the only goal. The other goal is also to have really short signatures so that the scheme can be amenable for many applicable for many practical applications. So for instance, for the vehicle-to-vehicle communication system I mentioned before, bandwidth is really one of the tightest constraints. And as I'm going, and actually the group signatures that have been proposed so far actually do not even fit those constraints because they all rely on encryption. So the first contribution of the paper is our security definitions. So in the threshold setting for group signatures. So this is a setting in which the authorities are corrupt at the beginning of the game. So the authorities are statically corrupt, but of course the users can be dynamically corrupt. And we also assume key generation to be fully non-trusted. So there's no trust assumption in the generation of the keys. And the anonymity requirement is now that as long as TO out of NO openers, at most TO out of NO openers are corrupt, then no information about signers should be inferred. And the definition also introduces a parameter TI star for the number of issuers that can be corrupt in the game. And of course, the strongest notion would be to assume that all issuers are corrupt in the anonymity game. But requiring in the definition certain issuers to be honest can actually lead to more efficient schemes than otherwise. And similarly, traceability is also defined. And now the definition just says that as long as TI out of NI issuers are corrupt at most, then no efficient adversary should be able to forge valid signatures. And there's now also, again, a threshold and parameter TO star for the number of openers that can be corrupt for the same reasons as before. The second contribution of the paper is actually a practical scheme that is fully threshold, so which has thresholds, issuance, and traceability. And the signatures are relatively short as they consist of only 2 first group elements and 3 exponents. And the signing and verification costs are also relatively low. The main upshot of the construction is to manage to sort of salvage the get shorty idea, which is due to a paper from Bixel et al. In 2010, which uses no encryption, but rather uses information during issuance to be able to open signatures later. So which means that in the construction, the identity of signers is not encrypted under an opener's key, but actually there's just no attached ciphertext. So this really makes the signatures really short. But the main challenge here was to make first, to sort of have this idea in a threshold setting, but also the other challenge is to be able to separate issuers from openers, because as I just explained, opening here works by keeping some information, some state during issuance that later allowed to open signatures. And here we actually did manage to separate issuers and openers, but still have signatures are short. And as another contribution, we also developed group signature schemes for multi-signatures. So meaning that here the membership credentials that users will get from the issuer are not just signatures now, but they are multi-signatures from all the issuers. And the multi-signature at stake in question here is a new Puerto Alessandro's multi-signature scheme. And a nice feature about it is that it allows for efficient zero-knowledge proofs of knowledge of signatures, of multi-signatures. Then the downside of this construction is now that all issuers must participate because it's a multi-signature scheme, meaning that all signers must have signed to other user. But the benefit now is that then we can tolerate the corruption of all the issuers but one, and not just half of them as before. And the scheme still also supports threshold opening. And that's it for this presentation. Please have a look at the full video for more details about the main ideas of the scheme. And please, send us an email if you have any question.
Thank you very much, Patrick. We are kind of running out of the time right now, but we could still have several questions. So maybe you can also first stop sharing your screen. And then I have like just maybe a very general question. So you had a table where you stated the efficiency of your own scheme. Can you kind of compare like what is the relation with most efficient competitors?
Okay, so first, the thing is that we are the first, no, we're not the first team. So there was another paper by, I think, Gennaro and other people that had threshold issuance and threshold opening. But there, the main difference is that their ciphertexts are much larger, because what they do is basically they use this encryption idea. So encrypting the identity of the signer under the opener's key. And what they do basically for threshold opening is the standard idea of distributing the threshold decryption key. And this makes the ciphertext much larger. So our signatures are actually much shorter. The other, so it depends really on which curve you're going to instantiate the schemes, but our signatures are much shorter. The other schemes which are as short as ours were not threshold. So for instance, the scheme of Poinçon and Sanders from 2016, which is just an adaptation from the scheme of Pixel-Leal, had signatures which actually were of similar size, but the only difference is there that they have a single authority that is responsible for both issuance and opening. So the scheme was not threshold at all. I hope this helps.
Okay, and then maybe a nasty question. Is your scheme applicable in blockchain? And if not, what is the main application you have in mind?
Okay, so for the group signature scheme, the main application was that we had actually motivated to work was vehicle-to-vehicle communication systems. But you can also think of TPMs, for instance. But for blockchains, I would assume that the multi-signature scheme could actually have very interesting applications, because there you can easily prove knowledge of multi-signatures. And the signatures are also short. So like, for instance, there was a BLS multi-signature scheme in 2018 and there's a crypt from Bonnet and Neven and drivers. But there you couldn't, for instance, prove easily knowledge of multi-signatures, whereas here that we can. So the multi-signature scheme could have applications, I think, in blockchain technologies and other privacy-preserving applications.
Thank you very much. So we should start the break now. So Vlad, Clemente, what's your opinion? Should we have a short panel with all participants, or what should we do now? Or some more questions to Patrick?
Well, I think that if there are questions, of course, we can take questions. Otherwise, we can start, stop for 10 minutes just to grab a coffee. Helge, if you have questions on the chat, please go on. Otherwise, we stop.
I haven't seen any questions on the chat. So, Vlad, you have questions?
No, I just rejoined to see, to answer or discuss if should we stop the recording or not. I didn't have a question.
So should we have some kind of a short panel now?
Well, it's just a break, and we prepare for the next session, and we check with all the maybe authors of the next session, and do we have a chair? Was it Pino?
Yes.
Who was the next? Yeah.
Yes, Pino is here.
Okay. Then I guess we can finish this session.
Okay.
So Clemente, you decide if you want to have one recording, or if I guess you can pause the recording and then resume.
I can just pause recording and then restart, right? Vladimir, Pino?
Hey, Pino is here.
Okay.
Should I take over?
Yeah, Pino, the floor is yours.
Okay. Hello, everybody. Welcome to the second session of the day. It's about theory and lower bounds. So the first talk is anonymous symmetric key communication. It's joint work by Fabio Banfi and Willy Morer. And I guess Fabio is giving the talk, right, Fabio?
Yes, I'm here. Can you hear me?
Yeah. Very nice to meet you.
Great.
And you have 10 minutes total, so 5 plus 5, 6 plus 4, whatever. Okay.
Yes. So I start.
Okay. I see your slides. Perfect.
Great. Okay.
Thank you, Fabio. Go ahead.
Thanks. So thank you for the introduction. So let me explain in 5 minutes what we did. So again, my name is Fabio Banfi, and this is joint work with Willy Maurer from ETH Zurich. So we wanted to study the anonymity of probabilistic encryption and authenticated encryption. as opposed to nonce-based encryption and authenticated encryption. So for the latter, for nonce-based authenticated encryption, recently Chan and Rogaway wrote a paper. And so essentially for nonce-based AE, it's actually easy to see that it's not possible to provide anonymity right away because of the nonces. In particular, the nonces might leak information about the identity of the sender. So for this reason, they construct a new object, a new syntactic object, which is similar to NAE, but is a bit more complex. And they also provide a transformation from any nonce-based AE scheme to this new scheme, for which it is possible to provide, to show some form of anonymity. So while we study instead anonymity of probabilistic schemes, so first of all, we argue that they are conceptually easier and also much more suitable for a context where anonymity is important. And moreover, it also we also show that they actually can closely capture some real-world implementations. So in fact, if we think of TLS version 1.3, there's a nonce-based AE scheme used there, AES GCM, where actually the nonces are used in a somehow non-standard way, namely they are randomized. And this means that mathematically we can model such a scheme actually as a probabilistic authenticated encryption scheme rather than usual nonce-based one. And in particular, this means that our results apply to this class of nonce-based authenticated encryption schemes. So let me start now by showing the game-based security notions for PE and PAE enhanced by anonymity. So for encryption, usually we require confidentiality, which we can model mathematically as a distinction problem, namely the distinction problem between a system that encrypts normally messages for a fixed random key and one system which instead encrypts random messages for some random key. And we call usually this notion INCPA. For authenticated encryption, we also additionally require authenticity, and we can again formulate this notion as a distinction problem. Now we have to distinguish two systems, one being encryption and the other decryption, and in the real case, these are normal encryption systems. And for the ideal case, we have fake encryption, again, as before for encryption, and also fake decryption, where the fake decryption system simply always outputs the bottom symbol. And this notion is usually called in literature INCCA3. So the implicit assumption in this kind of definitions is that they should be used in a context where there is one sender, one receiver, and one eavesdropper. But in the real world, we actually might use such schemes in a different setting, namely where we have many senders and one receiver. Think of a server which communicates with many clients. So in our paper, we generalize this to the case of n senders, which I keep equal to 2 in this presentation for keeping things easier to see. And in this new setting, we are interested also about anonymity, because anonymity is a property that lives in a space where we have more than one sender intrinsically. And we model this as by indistinguishability of keys. So for encryption, additionally to confidentiality, we also require indistinguishability of keys. And we can model this formally as a distinction problem again, but not between a system implementing encryption for one key, but for two different keys, two independent keys, or the same key. And again, replacing messages by random messages when encrypting. And for authenticated encryption, similarly, we have a new distinction problem, where again, on the one hand, we have normal encryption and decryption for two independent keys. And on the other hand, we have fake encryption and decryption, and crucially for the same key. We also define composable definitions of anonymous security for PE and PAE. And for this, I need to briefly introduce the concept of anonymous channels. So we have the anonymous channel first here, where we have two senders on the left that input messages, which are output directly at the adversary interface on the bottom. And the adversary can also inject messages which are then received by the receiver. And a better channel is the anonymous authentic channel, where now the eavesdropper is not allowed to inject messages anymore, but it can still eavesdrop on what the two senders send. And crucially here, the receiver will see the identity of the sender, so it will know whether the message comes from the sender 1 or sender 2, but the eavesdropper will not. And this is how we model anonymity here in this context. And then a better version is the anonymous secure channel, where the eavesdropper cannot even see the content of the message anymore. At least he can possibly see the length of the messages, but not any partial information about the content itself. And then we define composable security and anonymity for encryption as the notion of constructing a secure channel from the authentic one and some appropriate key resource. And more formally, we define this as the existence of a simulator that such that if we apply encryption to this authentic channel with the keys, then this is indistinguishable from the secure channel where we simulate the strategy of the adversary appropriately in the simulator. And analogously for authenticator encryption, we define security and anonymity as the construction of the secure channel, not from the authentic, but directly from the insecure one, which we mathematically again formulate as the existence of a simulator such that these two systems are computationally indistinguishable. So in conclusion, our contributions are as follows. We provided game-based anonymity definitions for PE and PAE. Then we also showed that actually the stronger notion of pseudorandom ciphertext implies anonymity. We formally show this. And this also allows us to argue that NAE with randomized nonces, as I mentioned in the beginning, provides anonymity. And we also show that the interesting result that encrypt and MEC preserves anonymity. And then in the second part of our work, we also provided composable notions of anonymity for PE and PAE. And the advantages of such definition is that they provide a better understanding of the application, in the sense that we can see somehow with this channel what really these definitions are about. And we also show in the paper that these new definitions are, the composable ones are implied by the game-based ones. And finally, we also show in the paper that they actually allow for more efficient protocols than known before for constructing a secure channel from the authentic and the insecure one. So this is all for the short presentation, and I invite you to have a look at the paper if you have more interest in our results. Thank you.
Thank you, Fabio. So I would like to ask if you have a question and you are not a panelist, you should push the Q&A button that you find in your Zoom. In the meantime, Fabio, just we have time for one quick question. Can you go back to slide 3 just to understand your notation?
Yes.
And here, like the, okay, so when you do confidentiality, you know, the INCCA3 definition.
Yes.
So what is the DPERP? You know,
yes.
So is that an oracle that always refuses to decrypt? Or?
Exactly, yes. So this is a bit of a, I didn't explain in much detail.
Yeah.
Please explain better. Yeah. Essentially,
so, but he has to take into account the output of the encryption algorithm.
Yes,
right?
Exactly. So this is somehow hidden in this notation, but is explained better in the paper. Of course, if I ask for encryption to this oracle, I get a ciphertext.
Yeah. So they communicate the two oracles.
Exactly.
Right?
So this essentially, I ignore this fact here, but these two oracles are actually are dependent. They're not independent.
Okay.
They share some state, and yes, they must know. So the decryption must know which ciphertexts have been produced by the encryption oracle, so that it can.
Okay. That's what I figured. Just wanted to check. And then you call it INCCA3. Is this probably stronger than in INCCA2, or is just?
Yes. Yes.
Okay.
There is a separation. This comes from a paper from Shrimpton. I think it's only on the ePrint is
Okay.
not published, but yes.
Okay. Oh, I didn't know that. Okay.
Yeah.
Thank you. Thank you. And we
Welcome.
don't have questions. And okay, Fabio, thank you very
Okay,
much.
thank you. So I'll stop sharing. Thanks.
Okay, thank you. And I think the next talk, oh, Mark, is that you? No? Mark?
Yeah, that's me. Hi.
Okay. Mark Abu, is that the
Yeah.
correct pronunciation?
Absolutely.
Okay, perfect. So the next talk is cryptographic divergences, new techniques and new application, joint work by Mark Abu and Thomas Prest, and Mark will give the talk.
Yeah.
Go ahead.
So hopefully you can see the slides.
Okay,
All right.
good.
Yeah. So I'm going to talk briefly about the paper that we wrote with Thomas called the Cryptographic Divergences, New Techniques and New Applications. So there's two parts to the paper. First, a theoretical one where we introduce a new kind of divergence. We call it the relative error over alpha, which has some nice properties. And then we're going to talk about two applications. First one is about security for prime number generators. And then we're going to talk about secret privacy in fully homomorphic encryption scheme. So first, a quick recap about divergence. So general setting is that you have an ideal distribution and a real one, and you know that some scheme is secure when you use the ideal distribution, and you want to know how many bits of security you're going to lose when you go from the ideal distribution to the real one. So traditionally, when you do that, the main tool you use is the statistical distance. Another tool that has been used recently is the Renyi divergence. So I will call the two definitions here. And so what's the main difference? That with a statistical distance, you have some sort of additive inequality. So this would require the statistical distance to be lower than 2 to the minus lambda. There's a typo here, where lambda is your parameter or your security parameter. And with a Renyi divergence, you get some sort of multiplicative type of inequality. And this requires that the Renyi divergence should be only of the order of 1 plus 1 over the number of queries so that you get the same level of security. Now, the disclaimer with the Renyi divergence is that this is useful for search problems and not for decision problems. So there are some papers that use Renyi divergence for decision problems, but naively, if you just apply inequality like this is only useful to assess security when you talk about search problems. So now, in the paper, we introduce a new kind of divergence. We call it the relative error over the alpha. So this is definition. The only difference with the Renyi divergence is that you have a -1 in the absolute value. And you can see that when alpha is equal to 1, you get 2 times the statistical distance. And when alpha is equal to infinity, you get the standard relative error. So it has some nice properties. It works really well with the Renyi divergence, and you get the same type of inequality. So you would require also that the relative error is lower, is of the order of 1 over the number of queries to have security. But the nice property that makes this divergence stand out is the amplification property that we show in the paper, which is that if you have some random function and you have a technical condition on the support, then if you have some condition on the relative error, if you iterate this random function, you're going to amplify the relative error. So that was already known for the statistical distance. It was shown by Duca and Stele in the paper in 2016. I'm going to talk about it later. And we show it for the relative error over the alpha. So this is a generalization. And the Renyi divergence does not have a similar property. So we believe that this will make this divergence stand out. So now I'm going to move on to the proofs. So first about prime number generators. So here by security, we mean that we want prime number generators that would act like random ones. So the first one going to look at is the priming generator, which was introduced by Brandt and Damgaard. It's a really simple generator, so it is used a lot in the industry. but there have been no security proofs yet for this algorithm. So the basic idea is that you sample a number and just add 2 to it until you get a prime. And you do that at most S times to have something close to uniform. And we show actually in the paper that the Renyi divergence of infinite order is asymptotically bounded by a constant. This means that in security proofs, when you go from the uniform distribution to prime inc, you only lose log of 2c bits of security. So you can do security proof with that, and you can show that this generator is secure. And equivalently, you can bound from below the entropy of the algorithm, which provides security against collision attacks. Now moving on to a second generator, the one from Fook and Tibushi. So this generator is a bit more complicated. You have a parameter epsilon, which is the fraction of bit you're going to sample again, and until you find a prime number. And so what you want is for epsilon to be as low as possible, so that you don't have you lose less entropy as possible. So in their original paper, what they showed is that the statistical distance between the generator and the uniform one can be made as low as you want, depending on epsilon, and under a conjecture from number theory. And we show that under the same conjecture, the same bound apply for the relative error over the alpha. So now remember that the relative error does not need to be as low as the statistical distance. So you get the same level of security for, we showed in the paper some computations, and you can roughly divide epsilon by 5. So that's it for the prime number generators. And now for the secret private fully homomorphic encryption. So the setting is that you have a client and a server S. Client has a message M and wants the value of F of M, and the server does the computation with a circuit. And the additional property that we want here is that the client does not learn anything from the server. So this is called secret privacy. So how do you achieve that? So Duca and Stelle in their paper in 2016, what they did is that they introduced a random function called the washing machine. And so they did this analysis with the statistical distance. And the idea is that you have some preliminary bound on the statistical distance, and you use the amplification property to get the desired bound for security. We do the same thing with the relative error here. So how does the washing machine work? Well, for example, for AWE ciphertext, so we're going to bounce back between two sets of AWE ciphertext, one with low noise and one with big noise. So to reduce noise, you use the bootstrapping process, which is deterministic and very heavy in computation. So you want to do it as less as possible. And then reround is the random function that will enlarge the noise and that will inject randomness. So how does it work? Is that what you do is that if you have a ciphertext, you just sample C prime with the process such that C prime is close to uniform. And then you add the noise F, which here will come from Gaussian distribution. In the original paper, it comes from uniform distribution. And you show that the only leakage of reround comes from F. And we show in the paper that we managed to achieve, to get the bound we want on the relative error. So when you iterate it k times, and k being of the order log of q, log of the number of queries, you get the wanted level of security. So in conclusion, we managed to divide the number of iterations of the process by lambda over log q, where lambda is the number of queries. So that's it, and I'll be waiting for your questions.
Thank you, thank you. So do we have a question for Mark?
Yeah.
Okay. Okay. So, so in your last slide, Q is the number of queries, and there is a logarithmic dependency. So, so can you put the last slide? It's log Q over lambda. Lambda is the security parameter, right?
Yeah. Okay. Yes.
And this is so as long as Q is polynomial in the security parameter, This is going to be what? Sublinear in the security parameter, right?
Well, in practice, since we're doing fully homomorphic encryption here, actually the number of queries is lower than usual. Like the security level should be around 256, for example, but log of Q, like the number of queries should be of the order of 2 to the 64, maybe, 2 to the 64 might be reasonable. 2 to the 128 might be a bit much for fully homomorphic encryption. So.
Okay. So you're listening on concrete numbers. So for lambda 256 and Q64, that's the okay.
And the Q is 2 to the 64. So yeah, here you would divide by 4 the number of iterations.
Okay. I understand.
Yeah.
Oh, so and this is your gain in the.
Yeah, this is the gain. Using our process. Now, the only difference is that we use the Gaussian distribution instead of the uniform distribution. So that might add a bit of time in practice if you want to implement this. But in theory, yeah, you would need less rounds.
Okay, I understand. And you're looking at the number of iterations, not at the cost of each iteration. Okay, that's good.
Yeah.
Okay,
yeah, that's why.
Okay, I think I understand now. Okay, and so time, let me see if there is, okay, no question. Okay. Oh, it's like I'm having my own private tutoring this afternoon. People came.
Well, okay, anyway, there's slides in the video online, so if people want to watch the full video with more comparison, they can do it.
So let me see if Mark is around. Maybe we can. Oh, no. The next one is Hendrik. Is Hendrik around? We can go to the next talk. Okay, Mark, thank you very much. And Hendrik?
Yep.
Hendrik. Okay. Hendrik, that's going to be Waldner or Waldner?
Waldner.
Waldner, okay, thank you. And okay, so the next talk is on multi-client inner product functional encryption in the random oracle model. It's joint work by Michel Abdallah, Florian Burs, Hugo Marival, David Poincheval, Azam Soleimanian, which I think I've seen in the previous session, or no? And Hendrik Waldner. And Hendrik, you have 10 minutes, including questions. Go ahead.
Thanks for the introduction. So let me start with giving you an overview of the primitive. So in multi-client inner product function encryption, we have a setup algorithm that outputs different secret keys for all participating parties and a master secret key. And the different secret keys can be used by here Alice and Carol to generate encryptions of their messages. So Alice would use the key number 1 to generate an encryption of her message X1 using the label L1. And Carol would use her key number 2 to generate an encryption of the message X2 under the label L2. And then if another party, Bob, receives these ciphertexts and he has a functional key associated with the vector Y, which is generated using this master secret key that the setup algorithm has output in the beginning, and a key generation procedure together with the vector that should be associated with the functional key, in our case, the Y. Then Bob is able to compute the inner product between Y and the concatenated messages of Alice and Carol under the additional condition that the labels that Alice and Carol have used for the encryption are the same. So in our case, this would be L1 equal to L2. And security in the setting holds if Bob doesn't learn more than the inner product that he's allowed to learn by having his functional key for the vector Y. Yeah, the first time that a construction for this primitive has been proposed was by Chotard et al. In 2017. They present a construction based on DDH in the random oracle model. And then there are 2 follow-up works from 2019. The first one by Abdallah et al. They present a black box compiler that takes a single input function encryption scheme and lifts it into the multi-client setting by assuming PRFs. Their construction is in the standard model, and since their underlying single input schemes can be instantiated using MDDH, DCR, or LWE. These are the assumptions that they need. And then at the same time, there was also work by Libert and T2, where they directly show how to construct multi-client functional encryption based on LWE. And in this work, we are also going to present direct constructions from MDDH, DCR, and LWE, but we are going to rely on the random oracle model. Yeah, and one might ask, why do we rely on the random oracle model if we already know how to construct the primitive from the same assumptions in the standard model? And the reason is that we want better efficiency and practicality. So for example, we have shorter ciphertext and shorter secret keys. So now I can give you a generic overview about how our constructions work based on the different assumptions. So we first have a setup algorithm that generates the different secret keys for all the participating parties. And then the master secret key simply contains of all of these secret keys. And then the setup algorithm outputs the secret key to the corresponding party. To then generate an encryption of a message under label L, what we're first going to do is we're going to query the random oracle on this label. And then we use the secret key together with the random oracle output to generate a key KIL. And the function that is going to be used to do this depends on the underlying hardness assumption, so it differs. And then we can use this key KIL together with the message XI to generate the final ciphertext. Yeah, for the generation of the functional key for vector Y, what we're simply going to do is we're going to compute the inner products between all the secret keys of the parties and the different parts of the vector Y. So what we can do is we can split the vector Y into n different parts. And then the functional key is basically the sum of all the inner products of these secret keys with the different parts of the vector. This functional key can then be used for the decryption procedure. So if we have ciphertext from all the different parties, our functional key, the label, and the vector Y, we can query the random oracle again on the vector, on the value L. So we're basically proceeding similar here as in the encryption procedure. But for the second step, instead of using the secret key, we're going to use the functional key, and we apply the same function f on the random oracle output and the functional key sky to get this key ky. And then together with the vector y and all the ciphertexts, we can compute the final inner product of x and y. And yeah, this concludes the overview of the schemes. Thank you for your attention. I'm happy to answer any questions.
Thank you, Hendrik. Thank you. You are 5 minutes, perfect. So I have a question about your primitive.
Yeah.
I think that your construction is private key, right? Yeah.
Yeah. So
because yeah, and yeah, the yellow key and the red keys and so on. So yeah. So what about the public key? Because I remember some time ago I was thinking about this problem, and it seemed to me, but you know, that's what I'm asking you.
Yeah.
That in the private key, in the public key setting, this primitive will be very trivial, right? Because the adversary has so much power.
Exactly. So there are actually a lot of primitives, let's say, in the setting. So we have from the normal single input setting, then we have the multi-input setting, where we don't really assume that we have keys for all the participating parties. So there we can, for example, have exactly one master public key, as you said, and then the adversary is very powerful, and he can create encryptions for all the remaining slots, and he can do possible mix and matches. And here we have exactly the restriction there, that we have different encryption keys for the different slots. And in addition to this, we also have the labels. So you can even enforce more restrictions for ciphertext generated for the same position.
Okay. Okay. So so this primitive doesn't make much sense in the public key setting. That's, you know, you're confirming this.
Yeah, there exist also schemes like where you're in the public setting and you have one key for all the different positions.
Yeah, but then, okay. And a related question is that Alice and Carol, so there is one place for Alice, in a sense that whatever Alice encrypts using the yellow key 1, is going to be the first components of the, so they cannot switch, right?
Exactly. And yeah, if in the setting you described, you can also switch.
Yeah, okay. No, but staying private key. So if you're allowed to switch, like saying that, I don't know, like whatever Alice encrypts and Carol encrypts, they can be, you know, X1, X2 or X2 or X1. Like, does it still make sense or?
Yeah, there's also a security definition for this, but then of course you have to ensure that you have an additional leakage, right? Because if you're in an indistinguishability-based game and you ask a challenge for one position, you have to make sure that under every functional key you issue, all the different mix and matches and things remain the same under both challenges. And here we have, in addition, as I said also before, the labels, right? So we can also enforce additional restriction with this, because we only have to ensure that under every label, these evaluations are the same.
Yeah. Okay. While, okay, I understand. So while in your case, the distinguishability experiment is some, it's clear, like the adversary cannot ask for keys for which the two challenges give different interproduct. Okay. So let me see if there is some other question. Okay, Hendrik. So hang around until the end. Maybe someone will ask some questions. And thank you very much.
Thank you.
I think now Mark is next, right? Mark, are you?
Yep.
Hey, Mark, how are you?
Hey, good. How are you?
Good.
Just open the slides.
Okay. It's 4:45. You have 10 minutes. Thank you. Go ahead.
Cool. Thank you for the introduction. So this talk is about secret sharing lower bounds, and what we show is that either the reconstruction will be hard or the shares are long if one considers the most general setting. And this is a joint work with Casper Green-Larsen, and we're both from Aarhus University. So what is a secret sharing scheme? In a secret sharing scheme, we basically have some bit string here represented as a small file, and we would like to split this file into a bunch of shares. And these shares should have the property that certain subsets of those shares should be able to reveal what was the originally secret shared file or bit string. But some other subsets should not reveal any information whatsoever about the secret shared bit string. And to define who can reconstruct and who cannot reconstruct, we usually need to define something that is called an access structure. So this is basically a set of subsets of the shares. And if a subset is in this set, then it's allowed to reconstruct, and otherwise it is not. And I guess the most popular access structure that one can be familiar with is the threshold access structure. So this is, for instance, the Shamir secret sharing scheme, where we simply say that for some parameter t, if we have t or more shares, then we can reconstruct. And if we have t-1 or less shares, then we learn nothing about the secret shared value. But there's also other access structures. So for instance, one can consider a graph, and one fixes a graph and fixes two nodes here highlighted in blue. And one could say that the shares correspond to the nodes, and a set of shares is allowed to reconstruct the secret if they form a path between the two blue nodes. And more generally, one can consider arbitrary access structures, which are called general access structures, where one can simply think of something like a truth table, where I have a list of, I have for every row, I basically have one possible subset. And then on the right, I either have a check mark or a cross to indicate whether this subset will be authorized. And then the corresponding access structure is simply the collection of all the rows with the check mark. And one of the main questions in this area is how efficient can we construct secret sharing schemes for different access structures? And here efficiency means how big do these shares have to be for realizing this primitive? And what we know is that if we consider general access structures, then we can realize it, but the shares are very big. So we know how to do it with basically exponentially large shares. And even getting something like 2 to the c times n for some constant c, which is smaller than 1, we had to work very hard, and this is a breakthrough result from the past 2 years. So in terms of upper bounds, we're basically in the exponentially sized regime for share sizes. And in terms of lower bound, we only have a slightly superlinear lower bound, which tells us that that there exists some access structure for which the share size has to be n log n. So as you can see, there's quite a large gap. And there is basically, I think, like a 20-year-old conjecture, roughly, or even older by now, that there exists some access structure where the share size necessarily has to be 2 to the epsilon n, where epsilon again is some constant greater 0. So there exists some access structure for which we cannot really have some truly efficient secret sharing scheme that scales well with the number of shares. So what do we show in this work? Well, in this work, we show a slightly weaker theorem statement. So here we cannot prove or disprove the conjecture. What we can show is that there exists some access structure such that either the share size has to be exponential in the number of shares, or the reconstruction function has to run in a time that is exponentially large in the number of shares. And kind of in terms of a practical consequence, this means that there exists some access structures for which we cannot have something that we can actually use in any practical setting. And I won't have time to get into the proof, but I'll just want to give like a very high level idea of how the proof roughly works. So the general proof idea is the following. So what we will do in the first step is we will define a set D, and this will be a set of access structures. And again, recall that an access structure in itself is a set of subsets, and D will now be a set of those access structures. And D will be designed such that it is extremely large, so it has a doubly exponential size. And now if we have this many elements in the set, then just to describe any element in the set, we will need an exponentially large description string. In the second step, what we do is we want to construct some form of a lossless encoding. Okay, so this encoding takes some access structure as input, so an element from D as input, and it outputs an encoded string. And we will construct this encoding based on a hypothetical secret sharing scheme that we have. And the idea will be that the quality of the encoding in terms of how big is the output encoding string will depend on the parameters of the secret sharing scheme. And from the kind of the first observation, we know that if we take any element in D, we cannot encode it beyond some exponentially large size because this simply follows from the pigeonhole principle. So if we show that there is a secret sharing scheme, if we show that given a secret sharing scheme with certain parameters, we can construct a certain type of encoding, and we know that we have something that is like the best encoding we can hope for, then we also know what is the best secret sharing scheme that we can hope for. And by basically combining those two observations, we obtain our result. And you can check out our paper, which is on ePrint, to see the proof and all the details that I kind of skipped right now. And thanks for your attention.
Okay, thank you, Mark. We still have a few minutes. Just to make sure I understand. So the previous positive results, the one, 2 to the CN by Applebaum, Bemel. So,
yes.
So those have polynomial time reconstruction, right?
No, I think they have an exponential time reconstruction. Because they cannot, otherwise the lower bound would. I think they work on on like CDS schemes, and the underlying thing should run in exponential time.
Oh, but exponential in what? In the number of participants or in the size of the?
In the number of the shares.
The number of okay. So okay, I see. So your result says that either it's exponential. When you say exponentially hard in your result, you mean exponential in n or in the size of the shares?
Oh, okay, sorry. So if I take a secret and I split it into n shares, then either the shares will be on average exponentially large in n, or the reconstruction function will run in a time that is exponential in n.
Oh, okay, good.
So if you're automatically this means that if you manage to construct something that has, let's say, slightly smaller shares, then you are guaranteed to have an exponential runtime for your reconstruction function. And this even holds if you allow the secret sharing itself to run in exponential time. This does not help you to overcome the lower bound.
Oh, the dealer. Yeah, but we don't care about the dealer because that's one. Yeah, usually we don't care about the dealer. Oh, I see. So you're saying something like that the share could be something like n square, but then in that case, it's n square and you have n shares, total n cube bits, and you'll have to run for 2 to the n.
Yes, exactly.
Oh, okay. Which will be quite surprising, which means that most probably the shares will be large, not the reconstruction.
Yeah, exactly. But unfortunately, it seems to be a very large step to go from this proof to proving the conjecture.
Okay. Yeah. This will be a huge conjecture, but okay, I see.
Yeah.
Okay, and so let me see if there is more time. Yeah, we have less than a minute. I think we. Okay. Thank you, Mark.
Thanks.
Thank you. And next talk will be. Okay.
Hey.
Hi. How are you?
I'm fine, thank you.
Okay. So is that Julia or Julia?
It's Julia.
Okay, Julia Hesse. She will present separating symmetric and asymmetric password authenticated key exchange. And you have the floor. Thank you.
Thank you. So can you see the see the screen?
Yeah. Perfect. Yeah, perfect. And I can hear you.
Okay, so this paper is about password authenticated key exchange, or PAKE for short. And essentially it shows that the two versions of PAKE, symmetric and asymmetric, cannot be obtained from the same minimal assumptions. So let me just very briefly tell you what asymmetric PAKE is. It's a protocol between a user Alice on the left and a server, for example, the server of some web service. And Alice registers with the server, who then stores her password in a secure way. So for example, hash together with a salt. And later, Alice and the server can establish a joint cryptographic key if and only if Alice remembers her password correctly. Otherwise, K and K prime here will be random keys. And this primitive is essentially a good choice for applications where you want to verify a password in a secure way, because a crucial property or crucial security property of asymmetric PAKE is that the server at Make Friends here does not learn which password Alice is using upon login. So this paper takes a closer look at the security of asymmetric PAKE defined in the Universal Composability Framework. It's a simulation-based framework where a real execution of an APAKE is compared to an idealized version of it. So to define security, we actually have to define what an idealized asymmetric PAKE looks like. So this is the blue box here. In this idealized version, the parties essentially just provide their inputs and they receive their securely computed outputs. So in this case, the password, once entered at registration phase and once entered at the key exchange phase, and both parties obtain the session keys. These keys, K and K prime, they will essentially match when the input password is the same as the login password. There's also adversarial interfaces which model attacks that we cannot avoid, such as an adversary just simply guessing a password, which is of low entropy and can, of course, be guessed in polynomial time. Also, password files can be stolen, and those attacks are essentially hard-coded into the functionality. So there's many protocols in the literature which are UC secure APAKEs with respect to the functionality that I just showed you. The main drawback essentially of all these constructions is their use of idealized assumptions. For example, a programmable random oracle. We have heard a bit about random oracles already. A programmable random oracle is a bit worse than a normal random oracle. It's essentially a truly random function where the simulator can determine arbitrary point value pairs that are essentially not taken yet. So this is why it's called programmable. Of course, such an oracle cannot be instantiated securely. On the contrary, the symmetric version of PAKE, where both parties would hold a clear text password, it's called a symmetric PAKE. This can be obtained already in the standard model. So let's come to results of this paper. So essentially, until today, it's not. I mean, it's conjectured, but it's not really formally proven whether this need for idealized assumptions in asymmetric PAKE is inherent. And in this paper, we cannot really answer this question because it would require us essentially to rule out existence from any non-idealized or combination of non-idealized assumptions. But we take a step essentially towards resolving this question. So what we do is we rule out the existence of UC-secure asymmetric PAKE from the same set of minimal assumptions that are enough for constructing symmetric PAKE. So in more detail, we show that a non-programmable random oracle model is not enough to obtain asymmetric PAKE. And we also show that our proof essentially carries over to the common reference string model, where all parties have access to a random string. So let me very quickly give you an intuition on how this proof works. So here you see a real execution of the protocol on the left, and the ideal execution with this blue. I have a mouse. So this ideal PAKE functionality on the right here. So we show that when simulating the password file, the simulator essentially runs into a so-called commitment problem. So first, the simulator is committed to the value of the password file, which you can see here. So this is the simulated version. And he has to output this value essentially without knowing the password. A distinguisher can then essentially check whether the file works with respect to the true password. And the crucial observation here is now if this check is essentially offline, so it is without interacting with the simulator or any other entity, then the simulator cannot resolve his commitment issue, and he is essentially trapped. So as you can maybe imagine, proving such a statement in UC is a rather technical thing, and it essentially allowed us to have a closer look at the functionality, so to revisit the functionality, and you can find all gaps and fixes to the functionality, which essentially happened along the way of proving this result in the paper. There's also a full formal proof of security of an APAKE called the Omega protocol from the literature, which is the first full proof of security for this PAKE. Okay, and with this, I'd be happy to answer questions.
Thank you.
Can you still hear me? It shows me that my internet connection is unstable.
Oh, okay. Okay, so let's see if there are questions. No questions.
Okay.
Oh, okay. Can you put it back? So your result. So this is for asymmetric, because I guess that for symmetric password authenticated key, what is the status? I'm not an expert here. So if you want symmetric password authenticated key exchange, so can you do it with non-programmable random oracle?
Yes, it's already in the standard model.
Oh, it's in the standard model.
Yeah.
Okay. Okay, so you are ruling out the possibility of having it with the non-programmable random oracle.
Exactly. Yeah.
Okay. Okay. So is this somehow related? So there is an impossibility result, I think, by Jesper.
Yes.
On non-committing.
Well, it's related, but it's a bit. So the impossibility result of Jesper is about non-committing encryption, and there essentially the kind of the attack that trapped the simulator is essentially that you send and send and send messages, and at some point the simulator cannot explain anymore. Yeah. And here it's really a bit it's more tricky because the password file, it's short. So essentially, already a CRS could be enough to explain a short password file. We don't consider like updating your password. It's just one password file, one short thing that has to be simulated. So it's a bit different regarding the techniques to prove this.
Okay. So you have to do more work. And yeah, just one last question. And so instead, if you have programmable random oracle, this should be possible, right? You know already?
Yes. Yeah, it's possible in the programmable random oracle model. It's possible in the generic group model, essentially.
Okay. Let me see if there is a question. Otherwise, yeah, we're a little bit. I think we saved 5 minutes. Okay, and thank you all the speakers. I think I'll call it a session. And okay, so we're going to have a new session like at 5:20 Amalfi time. And thank you all the speakers. And I think I'm going to pass it to Clemente/Vlad.
Okay, okay, you're right, you're a little bit behind. So I propose to restart at the time that is on the schedule. It is at 5:20.
So we'll just have a longer break, right?
Right. Okay, so we'll start in 15 minutes or something like this. I stopped recording.
Okay, thank you, Clement. So welcome to this session on theory and lower bounds. The first talk is a paper called Key and Argument Updatable QA NISIX, and it's by Helger Lippbach. Helger will give the talk. So whenever you're ready to share your screen, Helger.
Thank you very much, Mike. Let me find the window. I think this is the correct one. So, and press play. So, hi everybody. My name is Helger Lippmaa. I come from Simula UIB in Norway. This talk is about key and argument updatable CANISCs and probably has the largest number of IFNs in this conference. So I'm going to talk about something that is called quasi-adaptive non-interactive zero knowledge, or as I pronounce it, CANISC. In the case, CANISC is essentially a kind of a non-interactive zero knowledge argument where you have an additional language parameter. So you can imagine that your language depends on some parameter. For example, the parameter can be something like an Elgamal public key, and then the argument is about something that is related to this concrete public key. So there's some guy who generates this language parameter LPAR, sends it to another guy. Another guy is what is typically called a CRS generator, or common reference string generator, although I will mostly call it the public key. So the second guy generates a public key, and then both LPAR and public key are sent to prover and verifier. Now prover has an input X and a witness W, and wants to convince the verifier that X belongs to a language that depends on this language parameter. For example, is an encryption of 0 under this concrete language parameter as being as a public key of concrete crypto system. So this second public key that is created by not Gandalf, but somebody else, this is like more like CRS that enables you to create a proof with respect to LPAR. So the prover takes LPAR and PK as inputs and then generates pi and sends it to the verifier.
And Helger, can I interrupt for a second?
Yes.
We only see your title slide. It sounds like you're starting to talk about some technical stuff.
Very weird. Do you now see my second slide?
Yeah, I can see, not in presentation view, but I can see the slide. But something was not working.
Okay, I don't know. So I will, can you see it now? Second slide?
Yes.
Okay. So I will start again. There's an LPAR generator, there's a public key generator. Both LPAR and public key are sent to both prover and verifier, who based on that communicate with each other. Pi depends on LPAR and public key input and witness, and the verifier only has the input, but also has access to LPAR and public key.
It looks like, Helga, it looks like we're not seeing the slide building animations. We just have, we're stuck on whatever was the first slide to show. So maybe we'll just stick with this view.
Okay, I will just show this view then. Now you see the whole slide, I think. So, and as usually in the case of zero knowledge, you have a simulator who has an access to something that the prover doesn't know. In this case, it's a secret key corresponding to the public key or trapdoor corresponding to the CRS. But note that there's no trapdoor corresponding to the language parameters. The simulator just knows LPAR, secret key, and X. And trapdoor outputs a pi that corresponds to or that looks indistinguishable from the pi generated by the prover. And note that it is important that the simulator knows something that is not known by the prover, because otherwise prover could generate also a proof without knowing the witness. So one note is why we are interested in quasi-adaptive proofs is that because it gives us very good efficiency in certain cases. So for example, if you want to do subspace K-NISC, then you can do adaptive NISC where the proof length is linear in the dimension of the subspace, but you can do K-NISC where proof length is just one group element. So anyways, I already explained that something like CRS or public key is needed, but the question is, can you do something like with a smaller trust? Usually in the CRS model, it is assumed that the public key has been generated by a completely trusted third guy. So the first K-NISC was proposed in 2013 by Chotla and Roy. In their case, everybody has to trust both the guy who generates LPAR and the guy who generates public key. In this year, in PKC, we had a paper that decreased the trust. So this all follows previous work, like there's similar work on SNARKs done before. So in the case of K-NISC, our work was the first. So we posed an argument in the model where P doesn't have to trust nobody, and V trusts PK generator. And in particular, it's not necessary to trust the language parameter by either of them. So this is in some sense it's minimal that we can get. And this corresponds to the well-known pair public key model. You can think that the verifier just creates a public key and uploads it, and prover just uses this public key. The problem with this is that this scheme would be designated verifier, because if it's only one verifier who posts the public key, then other verifiers don't have to trust it. So there's a very recent model that is called Updatable NISC by Krot, etc. 2 years ago. And in this work, we are going to modify it so that it can be used together with K-NISC. So in that model, what happens is that you have a public key that is constantly updated by different parties. And the verifier just has to trust one of the guys who was updating. So this one guy can be herself, or it can be somebody who's just trusted by this verifier. Maybe, I don't know, in the election setting, you have that the key is updated by each political party, if you have more than one, of course. In more details, how does updating look like? In this previous model that was proposed for NARCs, you had two different public keys and the argument. So you had a universal public key that did not depend on the language. So SNARKs are usually about circuits. So universal public key does not depend on the circuits. You update it many times, and then at some moment you can decide to specialize the universal key to a concrete circuit. The nice thing in those constructions is that the specialization is completely public. It doesn't require the knowledge of the updating in secret key or updating trapdoor. It can be done by everybody. And then when you have this updated, like when you have this specialized public key, you can construct an argument based on this public key. There are several problems with this model still. One of the things is that while the specialized public key can just be recreated each time, you cannot update the argument. So when you generate a new specialized public key, you just have to create a new argument from scratch by using the witness. The second thing is that there's a well-known impossibility result, which basically says that if you do at least multiplicative updating, then this is only possible if the public key contains only monomials in secret values. And the latter is not the case when we work on CONISCs. So basically the results of this paper is that we construct an updatable version of the most efficient existing CONISC by Kiltsen V. It is, for subspaces, it's just one group element, the argument. Then very interesting thing that we achieve is argument updatability. Namely, instead of having to create new update from scratch each time when the public key is updated, you can use the secret information from updating the public key also to update the argument. So no other previous scheme had this property, and it's very interesting to see what are going to be the applications of this. We also, obviously, we propose corresponding security definitions. What does it mean to be securely key and argument updatable CONISC, etc. Then maybe the most technical thing that I'm going to explain about my result is that we have a very different updating strategies. Like I said, there's an impossibility result saying that if you do multiplicative updates, then the public key can only consist of monomials in trapdoors. And this is not the case in CONISCs. So we do something very different. Yes.
Can I interrupt? I think we're running a bit out of time. I want to make sure we have a chance for any questions.
I mean, this is basically the last slide. So.
Great.
So the public key in our case is Kiltsen V public key is divided into two parts. One of them is this universal key, and another one is this specialized key. The interesting thing here is that the universal key is just a Kerr MDH hard matrix. So in the common case, it could be just 1 times 1 matrix or one group element. And the rest depends on the concrete subspace, concrete language. So how we do updating is that we update this universal matrix by doing matrix multiplications. And we show when exactly does it work. So it means that this matrix has to come from certain nice distributions, but all interesting distributions actually belong to this set. And then we update the the subspace dependent public key additively, and that's it. So this is how we avoid this impossibility result. And then I think the very interesting thing here is generalization, because this universal public key is just a Kerr MDH hard matrix. It does not depend on the fact that we are doing CONISC at all. So if you have any peering-based application where your security relies on Kerr MDH, maybe in all those applications, you could just use single matrix that has been updated by, I don't know, some blockchain or whatever. And when you are interested in a new application that uses it, you just specialize. And like I said, together with specialization, you can also update the proofs. So that would be all. Thanks.
Okay, thanks, Helger. we're a bit out of time for questions. So I would just ask if anyone has questions for Helger, use the Q&A feature. And I should have mentioned at the beginning, you can use the Q&A feature for all of the talks. But thanks for that talk, Helger. And we're going to move on.
I think we have lost Mike. Maybe we may just wait if he managed to connect again.
Somebody dropped the mic.
Here he is. No.
Mike was frozen and he's coming back now. Okay, nice.
Hey guys, I made sure I did this from my office so that I wouldn't have internet troubles. Sorry about that. So I don't know if you heard me try to introduce the next talk. I think in the interest of time, we'll just let Roberto take it away if you're ready to start sharing your slides. This is a paper by Michele Ciampi, Roberto Parisella, and Daniele Venturi. And Daniele is giving the talk. Roberto is giving the talk, sorry. Go ahead. You have to unmute yourself.
Okay, can you hear me?
Yes. We lost your screen share. It's coming back. Perfect. Sorry about the technical difficulties.
Yeah, don't worry. So I'm going to present my work. The title is On Adaptive Security of Delayed Input Sigma Protocol and Fiat-Shamir-Nitsk, and I did it with Michele Ciampi and Daniele Venturi. We deal with Sigma Protocol, which I recall briefly are 3-round interactive proof of knowledge. So there is an algorithm called prover that has to convince another algorithm called verifier that it has a pair of statement witness. And one of the features is that the second message, the only one sent to the verifier, from the verifier to the prover, is just some randoms. And so it's a public coin proof of knowledge. We can define this protocol directly in the CRS model, which means we suppose the existence of a trusted third party that compute a common reference strings and makes it available to both prover and verifier as additional input. Canetti, Lombardi, and Weeks works with a particular class of Sigma protocols defined by having a property called trapdoorness. And they use this protocol to instantiate non-interactive zero-knowledge argument via the Fiat-Shamir transform, which I recall here in the slide, is a general transform to define a non-interactive argument from any Sigma protocol using an hash functions and letting the prover compute the second message, hashing the first message. Due to a famous impossibility result, Fiat-Shamir transform is unconditionally secure only in the random oracle model. However, Canetti, Lombardi, and Weeks recently showed that if we start from a trapdoor Sigma protocol, and if we use a family of correlation introtable hash functions, we soundly instantiate a NISC. But this left us with two important open questions. The first one is about the trapdoorness property of Sigma protocol. We would like a compiler to define a trapdoor Sigma protocol from any Sigma protocol. And the second one is about how to define NISQ with either adaptive soundness or adaptive input, no interactive zero knowledge with this kind of frameworks. In principle, we already knew that we can apply these frameworks to the Lepidot-Shamir Sigma protocol for a Hamiltonian graph and obtain a NISQ with adaptive security. So we could use CARP NP reduction and define a NISQ with this kind of security for all NP languages. However, CARP reduction are very inefficient objects. They cannot be used in practice. So in this work, we show how to do that without NP reduction. The first result is that we notice it, that applying a slightly different Fiat-Shamir transform. So as we can see in the slide, computing the second message, hashing the statement X concatenated to the first message. With this framework, we define a NISQ that has adaptive non-interactive soundness. On the other hand, applying the standard Fiat-Shamir transform and letting the starting Sigma protocol as another property called adaptive input honest verifier zero knowledge, we define a NISQ that has non-adaptive soundness, but adaptive input non-interactive zero knowledge. The third and the most technical of our result is a general compiler to add this property of adaptive input honest verifier zero knowledge to any Sigma protocol for which this property makes sense, which is the class of delayed input Sigma protocol. This compiler is based only on the DDH assumption, and I stress the fact that this result is important on its own for some application, not only because how it's related to the NISQ framework. Then we have a general compiler to define a trapdoor Sigma protocol from almost any Sigma protocol. This compiler works using as additional tool a perfect correctness public key encryption scheme, but has to restrict the challenge space to only 1 bit length. However, this compiler doesn't preserve the delayed input property. So to complement this result, we have our last compiler that adds adaptive input honest verifier zero knowledge to any delayed input Sigma protocol, but preserving the trapdoorness property. And this compiler is built exploiting the property of a new commitment scheme called extractable IDTC, also defined in this work. Thank you for your attention.
Thanks, Roberto. If there are any questions, I'll just remind the participants to use the Q&A feature here on Zoom, and I will relay those questions to the speaker. In the meantime, Roberto, I was just wondering if you could just say what these adaptive soundness, adaptive ZK properties are. What is the adaptivity that you're referring to?
Okay, relative to the NISQ, adaptive soundness is when a NISQ, well, is that the adversary can choose the statement adaptively after seeing the CRS. So if a NISQ has adaptive soundness, no adversary can succeed, even if he can do that. And the adaptive input non-interactive zero knowledge is defined by the existence of a two phases zero knowledge simulator for the NISQ scheme. The first phase doesn't have the statement as input and has to compute a valid CRS, a CRS indistinguishable from an honest generated one, along with the trapper. Then the second statement receives the second phase receives the statement and has to compute a valid proof. And then this property of adaptive input honest verifier zero knowledge is for delayed input Sigma protocol, which are Sigma protocol for which the first message is independent from the statement. So in principle, an adversary can choose the statement adaptively after seeing the first message and the challenge. This property ensures us that the zero knowledge adversary can do that. So once again, we have a two-phases simulator. The first one is holding the challenge but not statement, and has to compute the first message. And the second phase is receive the statement and has to compute a valid third message.
Great, thanks. We have a question in the chat from Willie. He's wondering whether your construction preserves statistical soundness or statistical zero knowledge. Can you use your construction to get adaptively sound statistical zero knowledge, for instance?
You mean the non-interactive zero knowledge, or you mean for Sigma protocol or for NISC? Because for the Sigma protocol, I think we can't, because the compiler strongly relies on the DDH assumption.
Okay.
For NISC, I think since the compiler is almost black box, it depends on the primitive you used. So if you use a family of correlation intractable hash functions that has statistical security, and if the adaptive input honest verifier zero knowledge property is statistical secure, and also if the trapped honest property is statistical secure, then I think you can obtain statistical security.
Okay, great. Thank you. So let's move on to the next talk. Thanks again, Roberto. The next talk is on the round complexity of secure computation against covert adversaries. It's a paper by Arka Rai Chaudhuri, Vipul Goyal, and Abhishek Jain. Arka will give the talk. Looks like we're all ready. Go ahead.
Yeah, can you hear me?
Yes.
Awesome. Okay, so today I'm going to talk about our work on the round complexity of MPC protocols against a special class of adversaries called covert adversaries. And this is joint work with Vipul and Abhishek. So MPC protocol, what are they? So MPC protocol is a mechanism that allows parties that have some private inputs to jointly compute some function over their private inputs. They do so by running protocols, which involves exchanging messages, at the end of which everybody just has the output of the protocol. So since we really care about round complexity, what is a round? So a round simply constitutes of every participant sending a message. And the goal for efficiency purposes is going to be to minimize the number of rounds of interaction. So security, intuitively, we are going to say that even misbehaving participants shouldn't learn anything beyond the output of the function. And we'll get back to the security momentarily. Okay, so since we care about round complexity, what do we know about round complexity of MPC protocols? So we know if we only consider protocols that are secure against adversaries that behave honestly, but just try to glean information from the protocol, these adversaries are called semi-honest. We know we can construct two-round protocols, which are tight. And for the other setting where we say, okay, the adversary can behave arbitrarily, we know of four-round protocols, which are again known to be tight given three-round impossibilities. Great. So we have semi-honest protocols that we know how to construct in 2 rounds, and malicious, which are 4-round protocols. So given the state of the world, the question that we ask is, can we design protocols that sort of spans the spectrum? So we have 2-round for semi-honest and 4-round for malicious, with some intermediate security notion, hopefully with some tunable parameter, which we can set accordingly. So what is this intermediate security notion that we consider? For this work, we consider the notion of covert adversaries. And these are adversaries that behave maliciously if they can do so undetected. So since this is not a common security notion, let's actually see what covert adversaries are. So in general security, in general protocols, we say a protocol is secure in the real world, and we contrast it with an ideal world where all the parties just send their inputs to some trusted functionality who computes the output and sends it back. And we say, hey, a protocol in the real world is secure if any adversary corrupting the parties in the real world, there is a corresponding adversary that corrupts the same parties in the ideal. So this is the typical notion for security. The covert adversary notion gives the adversary a little more power, and this was introduced by this work by Aumann and Lindell. And here the adversary can send a special message, cheat message to the trusted functionality, upon which the trusted functionality collects all the honest party inputs and sends it to the adversary. Great. So this is the cheating adversary, and we said an adversary doesn't want to get caught. So how is that modeled? And that's modeled by flipping a coin. And with probability epsilon, which is called the deterrence factor and is like a system or security parameter, we end up in the left world where the trusted functionality tells all the honest parties, hey, the adversary sent a cheat message. And with probability 1 minus epsilon, we end up in the right world where the trusted functionality doesn't tell the honest parties anything. In fact, to rub salt into their wounds, it lets the adversary choose an output of its choice, which the adversary says, the trusted party tells the honest party, hey, here's your output. So staring at this for a moment, you can see by setting epsilon equal to values between 1 and 0, you can go from cheating always being detected to cheating never being detected. So you can have sort of a tunable parameter for a security notion. So given this, we can recast our question as asking, what's the precise round complexity of protocols in the presence of covert adversaries? And I said, I showed you prior results for semi-honest malicious. What do we know for covert adversaries? Unfortunately, the best known results are those that achieve the stronger notion of security against malicious adversary, which is 4 rounds. And this is primarily because prior works focus on computational and communication complexity rather than on the round complexity. Great. So what are our results? We first show a negative result showing that you can't hope to have a 3-round protocol even against covert adversaries. Okay, so we have a negative result, so that rules out 3-round protocol. So what can we conceivably hope for from a positive result? We actually show a variable round protocol that in the presence of covert adversaries has an expected number of rounds that's 2 plus 3 times some function, and this function takes values between 0 and 1. So there's a lot going on in this positive result. Let's just pass this result. So the inputs to the function are n, which are the number of parties that participate in the protocol, and epsilon, which is the deterrence factor that you just saw. So it turns out in the best case, our protocol gives 2 rounds for epsilon equal to 0, and this corresponds to semi-honest adversaries, while in the worst case, for any epsilon greater than 1/2, we have a 5-round protocol. It should be noted that both the best and worst case are for honest participants, and an adversarial participant can always force a 5-round protocol and can actually do so without being detected. So this is, a problem. So can we at least mitigate this by saying, okay, can we at least have a worst case protocol of 4 rounds? And it turns out that similar ideas to our work actually can apply to 4-round protocols, but given the complex nature of current 4-round constructions, there's a little more work there. But, can we actually do anything about this adversary forcing 5 rounds? And it turns out that we can't. That's the first question. And it turns out that our protocol, the adversary can actually force 5 rounds, but if it does so, it won't be able to cheat covertly. So there's a trade-off for the adversary there between forcing 5 rounds and being able to cheat covertly. Yeah, and that's all I have to say. You can see my long talk or the full version of the paper for details, and yeah, I'm happy to take questions now.
Thanks, Arka. There's no questions in the Q&A yet, but I have a question. There are a couple different definitions of covert security. There's one where the adversary doesn't learn the honest party's inputs in the case that he's caught cheating. And which of these notions does your...
We have the weaker notion where the adversary always learns the output irrespective of whether it's caught or not. So the stronger notion is what we would ideally like to achieve. So that would get us closer to the malicious security for, say, epsilon equal to 0, where it's always detected if it tries to cheat. So we don't achieve that, but yeah, that's an open question. So we achieve the weaker notion of covertness.
Okay, good. And about malicious security, do the lower bounds for malicious security, do they rule out this kind of variable round protocol with expected number of rounds less than 4?
No, they don't. They consider concrete lower bounds, concrete round protocols. No.
Okay,
so,
yeah, that's interesting because you very rarely see variable round protocols where we talk about expected number of rounds.
Yeah.
If anyone thought of that when they were writing a lower bound?
Yeah, because typically the the randomness comes from whether you decide you run multiple executions and whether you decide to open certain executions or not. So at a very high level, our protocol either runs a very expensive check protocol or it runs a very short protocol without these expensive checks. And this is determined on the fly by all the parties. And that's how we get this expected round. It's either 5 rounds or 2 rounds. There's no in between. There's no like 3-round protocol. It never runs in 3 rounds or 4 rounds.
Mm-hmm. And it looked like for no matter what, if you wanted epsilon to be more than 1/2, you always have to pick the 5 rounds in the worst case.
Yeah, so it just every party sort of tosses a coin and determines if they're voting to go into this expensive check phase, and as long as one party decides, it's fine. This epsilon 1/2 also comes from the simulation, unfortunately, which is because you have to account for the fact that an adversary might not toss a coin with this epsilon probability, and you have to account for it. And so now you have to generate a transcript which sort of matching distributions, and that becomes a little tricky, and there's some calculation there which forces epsilon to be 1/2.
Okay, sounds good. So if anyone thinks of more questions, in the meantime, feel free to ask on the Q&A. Maybe Arka can stick around and
yeah, I'll be around.
Awesome. But good, thanks for your talk.
Thank you.
We'll move on to the next one. It's unprovability of leakage resilient cryptography beyond information theoretic limit. It's a paper by Rafael Paz. Go ahead, Rafael.
Can you all hear me?
Yes.
Excellent. And I assume that now you can also see the slides?
Yes.
All right, great. So hi, my name is Rafael Paz, and I'm going to give you a brief overview of our paper on provable security of leakage resilient cryptography beyond the information theoretic limit. So as the name suggests, this is a paper about leakage resilient cryptography. So what is leakage resilient cryptography? It's the study of cryptography in the presence of some leakage to the secrets of honest parties. And our focus is going to be on what's referred to as this bounded leakage model. So in this bounded leakage model, the attacker gets to see some arbitrary polymath computable function on the secret of the honest players, with the only restriction is that the output of this function needs to be of some bounded size L. And L is, for this to be non-trivial, L needs to be significantly smaller than the size of the length of the secret key L. We're actually going to be restricting our attention to the simplest task in crypto, that of a one-way function, and in particular the notion of a leakage resilient one-way function, or L leakage resilient one-way function. So what is such a one-way function? Well, this is easiest defined using a security game between a challenger C and an attacker A. And the game starts exactly like a one-way function game. We have the challenger first sampling some random X and evaluating the function F on this X, getting some output Y. And now the job of the attacker, of course, is to find a pre-image X to Y. But since we're considering leakage resilience, the attacker also gets to see some leakage on X. And this leakage, the attacker gets to specify by selecting some leakage circuits, Q1, Q2, Q3, and so on and so forth. And so start by selecting some leakage Q1, and it gets back this leakage function evaluated on the secret X. And then you can select another one, and so on and so forth. And eventually, the attacker, of course, is supposed to now find this pre-image X prime. And we say the attacker wins if, first of all, he manages to invert, right? And additionally, the total length of leakage needs to respect the leakage bound L. So summarizing, the attacker wins if he manages to invert using a bounded amount of leakage. So what's known about leakage resilient one-way functions? Well, the first thing that can be observed is that any one-way function or any one-way permutation is resilient to log n bits of leakage. And this simply follows that log n bits of leakage you can simulate on your own by just picking them at random, and you're going to be correct with probability 1/n. So any attack on leakage resilience can be simulated with just a 1/n security loss as an attack on the original one-way function. And the same argument can be used to actually show much stronger force of leakage resilience, even n3 epsilon bits of leakage resilience, if you start off with sub-exponentially secure one-way function or one permutation. But the question is, can we get leakage resilience beyond just log n bits if we just make polynomial hardness assumptions? And indeed, some very nice results by Katzenbein-Kontanatan and Alven, Dodis, and Vix from over 10 years ago show that actually we can get one-way functions that are leakage resilient even to n over 2 bits of leakage from just polynomial hardness. And what they show, among other things, is that if you start with a collision-resistant hash function that is just sufficiently compressing, so it compresses the input by a lot, that's going to be very leakage resilient. And the key point for why this argument works is that take your one-way function. If it compresses the input x, there is actually a lot of entropy left in x after you get the output of the function. In fact, even if you get the output of the function and additional leakage, there's still a lot of entropy left in the secret x. So really, to make this argument go through, we rely on the fact that the secret has a lot of actual entropy given the output of the function and after the leakage. And this principle is not just used to prove leakage resilient one-way functions, but it's actually, this is the key underlying principle in basically all proofs of non-trivial leakage resilience. You need to make sure that your secret has a lot of entropy left, even after, a lot of real entropy left after leakage. So the focus of this paper is whether this is inherent. Can we actually go beyond what I refer to as this information theoretic barrier? And can we also prove leakage resilience in situations where the secrets are only computationally hidden? So as a concrete example, let's focus on one-way permutations. Can I get a one-way permutation that is leakage resilient to just n to epsilon bits of leakage under polynomial hardness assumptions? As I mentioned, any sub-exponential secure one permutation is, but now I'm asking, can we get it based on polynomial hardness assumptions? Clearly, a one permutation, I cannot use this approach from before because a one permutation fully determines the secret, right? Given f of x, I know exactly, information theoretically, know exactly what x is. More generally, if this question is too hard, maybe we can relax a little bit and focus on one-way functions that have not just one preimage, like in the case of one permutation, but a bounded number of preimages. Such a one-way function, if I evaluate the function on input x, doesn't fully determine x, right? Since I might have 2 to the n to epsilon preimages, there's still entropy left in x after seeing the evaluation. But once I get n to the epsilon bits of leakage, now that is exactly sufficing to fully determine x, right? So is it possible to get one-way functions that's, with small number of preimages that handle n to epsilon bits of leakage? And now this is getting us exactly tightly to this information theoretic barrier, because we do know that when you have many preimages, when the function is very compressing, we can get it. So the main result that we show is that the answer to both of these questions is no, at least if you restrict your attention to black box security reductions from constant run interactability assumptions. So what's a constant run interactability assumption? It's just an interactability assumption that's modeled as a game between a challenger and attacker that proceeds a constant number of runs. Most of our hardness assumptions are actually just 2-run assumptions, like the assumption that a function is one way is just a 2-run assumption. You have a challenger selecting x, giving f of x, you're supposed to invert it. That's just 2 runs. But you can consider more general assumptions such as a particular scheme is witness hiding. If the scheme is constant run, that's a constant run assumption. So what we show is for any such constant run interactability assumption, if you have a security reduction R that's black box in the attacker, so it uses the attacker as a black box, any such reduction must actually constitute an attack on that interactability assumption itself. So formally, what we show here is assume the existence of collision-resistant hash functions. So our result is actually not unconditional. We make this assumption that hash functions exist, collision-resistant hash functions exist. And let f be any function that has a bounded number of preimages. In particular, has 2 to the n to the epsilon bounded preimage set sizes. And let c be any interactability assumption. So c is a challenger in the security game between a challenger and attacker. And what we show is that that if you have a black box reduction R for basing entry-DAPS and leakage resilience of any function f, so this function f can be fully constructed in a fully non-black box way starting from C. The only thing I require is the reduction R using the attacker as a black box. So if you have a black box reduction for proving entry-DAPS and leakage resilience of f on the hardness of C, in that case, there exists some other attacker B that breaks C. So in that case, this assumption C is broken. So this thing is broken. Right. So if there is reduction, then the assumption must already be broken. Let me end this off with a few remarks. There's a very nice result by Daniel Wicks from 7 years ago that actually shows a very similar result, except that it focuses on some restricted types of black box reductions. In particular, Daniel's result shows that shows an impossibility for reductions R that not only treats the attacker as a black box, but also treat the leakage function as a black box. Today, we actually have several types of proofs of security or proofs of reductions that actually make use of the leakage functions in a non-black box way. So our result removes this restriction and deals with reductions that also use the leakage in a non-black box way. I won't go into any details on how we show it, but there are just two ingredients that are interesting to point out here. So we rely on succinct arguments and PCPs as a crucial ingredient to prove this thing. And additionally, in order to deal with all types of reductions, we also going to rely on this thing called recursive rewindings that is originated in the context of concurrent zero knowledge proofs. Thank you.
All right, thanks, Raphael. I was wondering about, by the way, if any questions, please put them up on the Q&A. In the meantime, I was wondering about your leakage restriction was based on the length of the leakage. And do your results have anything to say about leakage classes of leakage functions that are based on complexity, maybe like low depth leakage under low depth leakage functions, or something like that?
No, it doesn't. And it's actually a very interesting question, and one could potentially hope to prove such a thing using this framework. And it all actually depends on the complexity. So I mentioned here that we're relying on these succinct arguments. So if you can construct succinct arguments with appropriate complexity, the prover, in fact, the complexity of the prover strategy in these arguments translates to the class of a leakage function that you need to deal with. So there are some deep connections in your question and the complexities proof strategies.
So it sounds like in your attack, you use a leakage function to carry out the prover in a succinct argument and
exactly
and run the interactive proof.
Exactly. So the leakage function is actually implemented. So if you look at the longer version of the talk, I go into detail on how we show it. But yes, exactly like Mike is suggesting, the leakage that we're having the attacker ask for is going to be to ask to get to hear an succinct interactive argument that the reduction knows a pre-image, and that is how we can show that any such reduction really doesn't really need to use the attacker at all, because the reduction needs to provide this proof. This proof requires showing that you know the pre-image, and then therefore the reduction does not really need to make use of the attacker at all, because anything attacker tells it, it must have known already. Now, formalizing that turns out to be kind of complicated, because the reduction might talk to the attacker in very sophisticated and complicated ways. And that's what leads to these problems associated with concurrent zero knowledge, because we need to extract these instances from these many concurrent instances that the reduction is starting with attacker. That was kind of super fast. But if you look at the longer version, I go into it in a little bit more detail.
No, that sounds about right for the short time frame we have here. Helger is asking a question in the chat. You talk about constant round intractability assumptions, and is that tight? Do you know of a counterexample based on some weird multi-round intractability assumption?
Yeah, so that's a great question. In fact, in the paper, we don't make this restriction. And actually, the formal statement in the theorem is that if the leakage, so if you replace here this thing by L of n, where L of n is greater than R of n times n to the epsilon, then impossibility holds also. And this now is replaced by R of n. So if you consider an R round assumption, we can actually show that if the leakage is more than R times n to the epsilon, then impossibility still holds. So this only hits the information theoretic barrier when when R of n is constant. To explain why we need this R of n times n to the epsilon, we'll just note that if R of n is equal to L of n, if the number of rounds in assumption equals the total length of leakage, then this game here is actually a security game. This is an L round game. All right, so if I'm restricting it to L of n bits of leakage, the number of communication round is bounded by L of n. So this whole one-way function leakage game actually is an L round assumption. So I cannot hope to extend it beyond that, because there exists a reduction, which is the trivial one, stating this is an assumption.
Right.
So it's, yes, it's not fully tight because, but in the two ends, it is tight.
Okay, great. Thanks, Raphael. So we're going to move on to the next talk. This is a paper called Impossibility of Strong KDM Security with Auxiliary Input. This is a paper by Cody Freitag, Ilan Komargodsky, and Raphael Pass again. Cody will be giving the talk. Go ahead.
Hi, can you see my slides?
Yes, I can.
Awesome. Yeah, so I'm talking about impossibility of strong KDM security with auxiliary input. I'm Cody Freitag, and this is joint with Ilan Komargodsky and Raphael Pass. So to start off, I just want to introduce the standard notion of public key encryption, where you have a key generation algorithm that outputs a secret key and public key pair, an encryption algorithm that computes ciphertext based on some message, and a decryption algorithm that then recovers the message using the secret key. And the normal notion of security we consider is what's called semantic security, which just requires that no polynomial time attacker can distinguish between ciphertext of a 0 message and ciphertext of a 1 message. But the key point here is that these messages are actually fixed, and then we require that the advantage of the attacker is a probability over a random secret key public key pair generated from the keygen algorithm. But this doesn't capture the case where the message themselves in this semantic security notion might depend on the keys. And this is actually important because it comes up in natural applications like encrypting your hard drive, or in a more theoretical sense, it has come up in constructions for fully homomorphic encryption. And so this raises an additional security consideration called circular security, where here we generate a random secret key public key pair. And in addition to semantic security, we require that a ciphertext of the all 0 string is indistinguishable from a ciphertext of the secret key. So semantic security we require to still hold even when encrypting, say, the secret key, like for a disk encryption type application. And we can generalize this even further to consider what's called key-dependent message security, or KDM security, where again, we're generating a random secret key public key pair and requiring for any efficient function f, ciphertexts of zeros are indistinguishable from ciphertext of this function f applied to the secret key. And the key point here is now we've extended semantic security so the messages can depend polynomially on the keys. So this raises a natural question: is there a reason to define all these other notions, or is every semantically secure scheme also KDM secure? And the answer to this is no. And in fact, it's easy to show that there exists an encryption scheme such that semantic security holds, ciphertexts of 0 and 1 are indistinguishable, but ciphertext of the all 0 string can be distinguished from a ciphertext of the secret key. But I want to point out that this does not imply that every scheme does not satisfy KDM security. For example, we do know of KDM secure encryption schemes in the random oracle model. We know of bounded notions of KDM security from various structured assumptions. This is where the class of functions that you're secure against, your encryption scheme can depend on this class in some way. And in fact, kind of the counterexample to KDM security that's kind of a folklore result, it seems very contrived, as the public encryption scheme specifically looks for the secret key and then does something kind of weird if it sees that it has an encryption of the secret key. So it's reasonable to think that most natural schemes are believed to be KDM secure. So we can kind of use this in applications like disk encryption, and it's reasonable for things like fully homomorphic encryption that such a scheme exists. So this gives us hope to use this in applications and moving forward. So motivated by this, I want to consider and put forth a notion called strong KDM security with auxiliary input that strengthens the notion of KDM security in a few ways. So first, rather than honestly sampling the public key, we're going to allow for a malicious distribution to sample the public key under the restriction that semantic security still holds. So it can't be so crazy that everything's lost, but we consider distributions where semantic security holds and ciphertext of 0 are indistinguishable from ciphertext of 1. Additionally, we allow for a public auxiliary input. You can think this is when the distribution or the adversarial player is part of a greater protocol. And so it's allowed to output, in addition to the public key, some auxiliary input, and still, because this is public, we require semantic security hold even in the presence of this auxiliary input. And lastly, the kind of key-dependent message security notion we require is that given such a distribution, we require that for any inefficient or exponential time function f, that ciphertext of zeros are indistinguishable from ciphertext of this function f applied to the public information, which might depend on the keys. So f can take as input the public key and the auxiliary input. We want KDM security to hold for any inefficient function f. And we didn't just make up this definition. This was actually used in a previous work to construct 2 message witness hiding protocols by Deshpande and Kalai in 2018. And I want to point out that in isolation, none of these modifications maybe seem too harmful. Like, it makes sense that as long as your scheme isn't contrived to break such a notion, maybe it could satisfy this strengthening of KDM security. So we ask in this work, does there exist such a scheme? And given the title of the talk, our main result is no. Specifically, assuming the learning with errors assumption and the existence of one-way permutation, we show that no semantically secure encryption scheme satisfies this strong KDM security with auxiliary input definition. And furthermore, even if maybe the auxiliary, you could argue that the impossibility maybe requires large auxiliary input or some other funny business going on, we show even with short auxiliary input, additionally assuming non-leveled FHE, that this impossibility still holds. And just to give a kind of really quick outline of what our proof looks like, so we start with any secure encryption scheme. And given this encryption scheme, we construct a distribution D and a function F such that semantic security holds in the presence of this public auxiliary input. Yet we can distinguish ciphertext of zeros from a ciphertext of this function F on the public key and auxiliary input. In the 2 ingredients we use a specific pseudorandom generator, which exists from one-way permutations. And we also use a special form of obfuscation for a compute and compare functionality that exists from learning with errors, the learning with errors assumption. So some takeaways I want to point out is that KDM security can be really useful, and maybe it's natural to kind of push the definition of KDM security a little bit and kind of rely on some assumptions and think that as long as my encryption scheme isn't contrived, it should satisfy this. But I want to point out that we should be careful not to push this too far, especially in the presence of auxiliary input. And in general, I think our work highlights that in many natural scenarios, even weak forms of obfuscation or obfuscation for simpler functionalities can be used to break security in the presence of auxiliary input, which I think we highlight in this work. So yeah, thank you.
All right, thanks for that talk, Cody. I'm going to let people formulate questions if they have some, but I have some questions. So you said that this strengthening of KDM security is not something that you just made up. It's used in this paper. to construct some two-message witness indistinguishable protocols, I think. And then you showed that this is impossible. So what happens to that result in light of your impossibility?
Yeah, so basically this was a preliminary result posted on ePrint, and we saw it, realized that not only did they need the normal definition they proposed, but also in the presence of this auxiliary input, which kind of broke, or at least broke the apparent assumption they used in their scheme. But as sometimes is used in these settings, maybe like if you don't just restrict the auxiliary input to be small, but you say, for this exact auxiliary input, we need security to hold, then maybe it's plausible it could be secure, but we kind of looked generally for any just bounded auxiliary inputs, this impossibility still holds.
I see. And you listed 3 strengthenings of this KDM definition. Is there any combination of those 3 strengthenings that, I mean, I assume you need all 3 of those for your impossibility to go through, but do you have any like positive results for, you know, any subset of those 3 strengthenings?
So I can flash the definition back up. So I guess I can point out that for the non-bounded auxiliary input setting, then the public key can actually be just honestly generated, but the auxiliary input needs to be generated in addition to the public key. So there's maybe some hope that there could be some positive things, maybe in a bounded setting where the public key is just an honestly generated public key. But yeah, I'm not sure of positive results. I guess one other thing is if the function f is efficient, then because we only allow the function f to depend on the public key and auxiliary input from this definition, this would actually just be a trivial implication by a standard reduction to just bitwise, thinking of bitwise encryptions. But the fact that this is an inefficient function f allows it to capture efficient functions of the secret key. And so maybe you could restrict that in some way and get positive results, but our impossibility makes use of the fact that this is an inefficient function additionally of the auxiliary inputs.
Okay. Great. Thanks, Cody. We're going to move on to the last talk in the session. This paper is called On the Query Complexity of Constructing PRFs from Non-Adaptive PRFs. It's a paper by Pratik Soni and Stefano Tessaro. Pratik will give the talk.
All right. Can you guys hear me well?
Yes, we can.
And see my slides?
Yes.
Okay, awesome.
Very good.
So, okay. So thanks for the introduction, Mike. Hello, everyone. Thanks for joining us. Our main result is a lower bound on the efficiency of constructing pseudo-random functions, or PRFs for short, from non-adaptive PRFs. And this is joint work with Stefano. So let's begin by defining PRFs. A function family f is a PRF if no efficient adversary can distinguish whether it is interacting with the function f under a random key, as in the left world, from a truly random function, as on the right. Note here that security is expected even against adversaries that ask all their queries adaptively. Non-adaptive PRFs are a relaxation which expects security only against adversaries that make all their queries at once or non-adaptively. Non-adaptive PRFs are clearly weaker than PRFs and hence may be simpler and more efficient to construct. Also, it is more reasonable to model AES as a non-adaptive PRF rather than PRF itself. Now, non-adaptive PRFs do end up implying PRGs, which imply PRFs. But here, our focus will be on direct constructions with the goal of understanding the complexity of such construction. Specifically, we want our constructions to make as few calls to the non-adaptive PRF as possible, be fully black box, and be security preserving with respect to all polynomial time adversaries. These 3 are well-studied targets in the design of symmetric key crypto. So there are 2 techniques to build PRFs from non-adaptive PRFs. First is the cascade construction due to Bellare, Canetti, and Kravchik, which constructs a complete binary tree, processing one bit of the input at every depth using the non-adaptive PRF, thereby making n calls. The number of calls can be reduced to any superconstant function using standard techniques. Second is the one-call construction due to Berman and Heitner. They show the construction that first pre-processes the input with a 2 universal family C and then makes one call to the non-adaptive PRF is indeed a PRF. But to show the polynomial time PRF security, they require the underlying non-adaptive PRF to be super polynomially secure. And hence, the construction is not security preserving. For some reasons, their construction is also not fully black box. They can make their construction security preserving at the cost of making super constant calls. So in summary, known constructions of PRFs from non-adaptive PRFs make super constant calls, and these have been seemingly hard to improve upon. We believe this to be inherent and take the first steps towards resolving this conjecture. First, we show a large class of one-call constructions do not suffice for this goal. A direct corollary of our result is that for one call, fully black box constructions must incur a super polynomial loss in security like the Berman-Heitner construction. We also lift our lower bound to arbitrary call constructions that make all their queries to the non-adaptive PRF in parallel. I would like to mention that previously such negative results were only known for the specific case of the composition construction, but here our focus is to rule out general constructions. So let's see things a little bit more formally, starting with our one call result, which considers this construction that pre-processes the input to the non-adaptive PRF and post-processes its output with function family C and G respectively. Here, we give a very general result, which says no matter what C and G are, the polynomial time PRF security of F cannot be shown from the polynomial time non-adaptive PRF security of H under fully black box reductions. But this requires the output to be sufficiently long. We can rule out shorter outputs and in fact even constant length outputs at the cost of making an assumption on the pre-processing function, which is basically a relaxation of the well-studied notion of universal hashing. In fact, by lower bounding the output length by larger and larger constants, it suffices us to make increasingly weaker assumptions on the pre-processing function. Finally, a word on our multiple call results, where we rule out constructions of this type, which makes all its queries to the non-adaptive PRF in parallel, whenever all the pre-processing functions are universal. I would like to emphasize that this result holds for any number of calls, generalizes a result by Myers, and complements a couple of known positive results. So this concludes the short talk. The paper will be on ePrint, and the link to the full talk is on the SCN website. In terms of open questions, clearly the big one is to rule out all constant call constructions or even obtain a 2-call result. And with that, I'll be happy to take any questions.
Okay, thanks, Pratik. That was a nice talk. I have a question about just a few slides back, you showed the parallel construction, yes, and it has an XOR at the end. So do you yes. only rule out constructions that are structured exactly this way with an XOR?
Yes.
I see. Is there a reason to, oh, go ahead.
So, sorry, can you finish the question?
Oh, I'm just wondering if there's a reason to, I mean, XOR is maybe certainly natural, but maybe you could think of some keyed function that maybe like some secret polynomial and you, or some universal hash of these things with a key.
So with that, I want to just give our one call result where we allow for this general post-processing, mm-hmm. right? Although in the paper, we don't show that, so the question you're asking is, can you replace XOR with a more general function? And yes. I believe we can, but one would need to work a little bit harder on the proof, which we do not show. So our main result is basically showing this construction, and then the techniques that we use for this end up extending to this multiple call construction. However, the question that you mentioned is actually a very cool question, but we do not address that directly in the paper.
Mm-hmm. And then sorry, I had another question about one of your theorem statements. You said you rule out constant. It was in a previous one with less details. You said that rule out constant number of calls, even arbitrary call. And I didn't. Can you clarify what that means?
Yeah, sure.
Arbitrary call parallel constructions.
So this result, so that part was talking about this result specifically. And here we show that the number of calls, which is denoted by L here, they don't need to be a constant. They can be actually a function of the input length n, and you could make polynomially many calls.
I see.
So it just says that this sort of combiner kind construction, no matter how many calls you make, is not going to suffice for this transformation.
I see. And what is the C that is constant then in that theorem statement?
So it's so we give a family of results which is indexed by some constant, and that constant sort of defines the assumption on the preprocessing function that we need to make. So if you think about constant as 1000, we get a better result because we now assume our preprocessing functions to be 1000 universal, which is a much weaker assumption than asking for it to be 2 universal.
I see. But presumably if you had a n universal preprocessing and you made n calls, then your theorem statement will not apply.
So yeah, our theorem statement only applies for constants. So
okay.
It's not clear because yeah, it's not clear what happens when you go beyond for even super constant preprocessing function, super constant universality. It's not even clear whether our result would hold. Yeah.
Right. Okay. Excellent. I think we're about out of time for the session. Thanks again to all the speakers for their excellent talks. Let's see. Clement wanted to say maybe one last thing in closing.
Yeah, thanks everybody for joining. It has been a great day. I want to thank the speakers and all the attendees that have been with us for all these 3 hours. So I'll see you tomorrow for the last day of the conference. Thank you very much for joining again, and see you tomorrow.
Thank you. Bye-bye.
Yeah, thanks so much.
Bye-bye.